A quiet channel exists in the present world, and its voice stays low, even and patient. It welcomes those who drift near it without naming them, as if the act of arriving requires no announcement at all. The room where listening happens varies from place to place, and the details are always ordinary cloth air, a dim corner of light, a window that holds back the day. The voice does not ask where anyone is because Earth already knows. It holds every location at once, and it keeps each one in place with the same calm gravity. The voice offers a gentle invitation anyway, not as a command, but as a simple opening, a slow walk into a subject that seems to disobey common sense, while remaining stubbornly real quantum entanglement, connection that keeps showing up in experiments even when intuition objects. The story begins far from laboratories and screens, in a time when Earth carries no quiet rooms at all. The Hadean Eon lies deep behind the present, more than 4 billion years in the past, and Earth's surface is not a surface in the modern sense. Heat dominates everything. Rock behaves like a fluid. The planet glows in places where magma reaches the open air, and even where it cools, it does not cool for long. Impacts arrive often enough to keep the young world unsettled. A rough rhythm of collisions that turns crust back into melt and throws vaporized stone into the sky. A scientifically accepted fact sits under all of it. Earth forms by accretion building mass from countless collisions of smaller bodies, and the energy of those impacts, along with radioactive decay and gravitational differentiation, keeps the early planet hot enough to melt extensively. Only a few 100 million years after formation, Earth is still working on becoming solid in any stable way. Only takes a planet-sized furnace to make ground a temporary condition. Above that restless heat, an atmosphere gathers that is nothing like the modern one. It is not a breathable veil, and it does not pretend to be. It is a thick exhalation of volcanic gases, an impact-generated vapor rich in water vapor and carbon dioxide, with nitrogen present and only trace-free oxygen. The sky does not have the familiar blue of Rayleigh scattering through a mild, dry air column. It is instead a complicated haze that shifts with temperature, composition, and dust. The sun shines, but its light meets a world that is still learning how to hold an atmosphere without constantly boiling it away. The young sun is fainter than the sun of today's stellar models, and multiple lines of evidence support a weaker early solar luminosity, yet the surface remains hot, a mismatch sometimes called the faint young sun problem. Earth, even at the start, specializes in contradictions that require careful accounting. Somewhere in that heat, matter begins to sort itself by density. Metallic iron, heavy and mobile under high temperature, sinks inward, and silicates lighter by comparison remain above. This differentiation is one of the defining processes of the early planet. A core forms, a mantle takes shape, and the energy released during segregation adds to the heat budget. A poetic detail hides inside this brutal sorting iron does not simply go down. It gathers like dark rain through a deep interior ocean of melt, forming droplets and streams that merge each merger, a quiet arithmetic of gravity. Only takes a few tens of millions of years for a core to assemble, and then it spends the next 4.5 billion years behaving as if it has always been there. The moon's presence is close in these earliest chapters, though its exact birth details remain one of Earth science's enduring puzzles. The leading hypothesis remains a giant impact, a Mars-sized body collides with the proto-Earth ejecting material that later accretes into the moon. Isotopic similarities between Earth and Moon, especially in oxygen isotopes, support a linked origin, yet they also deepen the mystery by making the event look oddly well mixed. The uncertainty is real and productive. How does a violent impact produce a satellite so compositionally close to Earth? And how does that process unfold in detail? How hot? How mixed? How fast? How much material comes from each body? Even in a story grounded in measurement, the earliest pages contain blurred ink. In that same universe, at that same time, physics holds a second kind of strangeness, one that does not require molten rock or impacts. Quantum mechanics describes the behavior of matter and light at small scales, where energy comes in discrete packets and systems occupy superpositions of possible states until measurement produces a definite outcome. Entanglement belongs to this regime. It is not a mystical thread and it is not a signal. It is a correlation in the joint state of two or more particles that cannot be explained by treating each particle as carrying its own independent set of properties. When such a combined state is prepared, the measurement outcomes remain linked even when the particles are separated. Experiments repeatedly confirm that these correlations violate the constraints of local hidden variable theories, and they do so in ways that match quantum predictions. Only takes decades of careful apparatus to demonstrate something nature has been doing all along without commentary. The dry irony is that the most famously connected phenomenon in physics is most visible when everything else is kept from touching. Entanglement is easiest to preserve when systems are isolated, cooled, shielded, and monitored, while the early Earth is the opposite of isolation. A planet-sized collision experiment unshielded and overheated, a place where interactions happen constantly and without subtlety. Another quiet irony settles beside it. The universe permits entanglement as a basic feature of its mathematics, yet it does not permit it to be used for faster-than-light messaging, so the strangest connection arrives with strict limits. A third irony follows. Patient and small human beings eventually build machines to protect entanglement from noise, while early Earth spends its youth inventing noise at an industrial scale as if that is the planet's first talent. Still, the Hadean Earth is not separate from the quantum world. Every atom in its magma follows quantum rules. The electronic structure of minerals, the bonding of silicates, the opacity of hot vapor, the absorption lines that shape radiative cooling, all of it rests on quantum mechanics. The story does not claim that early Earth behaves like a giant entangled pear. Instead, it keeps the connection modest and factual. Quantum laws underwrite chemistry and chemistry underwrites geology. In that sense, Earth's first crust is already a consequence of the same physics that later allows entanglement experiments to work. The difference is not in the laws, but in the conditions. A hot planet is a master of decoherence, the process by which quantum superpositions lose their phase relationships through interaction with the environment. In ordinary language, the world becomes definite because it cannot stop bumping into itself. Only takes a warm surrounding to make delicate correlations fade. The surface begins to show the earliest hints of what will later become stable continents, though the details remain debated. Some zircon crystals from Western Australia date to about 4.4 billion years ago, implying that some crust exists and cools enough for zircon to form, and that liquid water may already be present at least intermittently. Zircon is a hard, stubborn mineral, and it persists like a tiny memory chip of deep time, holding traces of oxygen isotopes and inclusions that suggest early interactions between rock and water. This is the lesser-known real-world detail that sits quietly in the palm. A crystal smaller than a fingernail becomes one of the few reliable witnesses from a time when most evidence is erased. Only takes a single durable lattice to outlast oceans of magma. Yet uncertainty remains everywhere. How early does stable crust truly form, and how much of it survives without being recycled? How quickly do oceans condense from steam atmospheres, and how often are they vaporized again by impacts? How does the early atmosphere evolve in composition, and what role do impacts and volcanic outgassing play in setting surface temperatures? Even the timing of Earth's first persistent magnetic field tied to core dynamics remains an active area of research. The mysteries are not decorative, they are the shape of the evidence. The voice stays slow as these processes linger. Stone is not yet a firm idea. Water is not yet a stable presence. Light arrives from a young sun and meets haze, dust, and vapour. The planet holds heat like a secret it cannot keep. And somewhere beneath every collision and every cooling crust, the underlying rules continue without negotiation. Quantum behaviour at the smallest scales, classical turbulence at the largest, and a boundary between them that refuses to be a clean line. Entanglement remains for now, a concept placed gently on the table, real tested, and strange like a pair of coins that keep matching even after being carried into separate pockets. The story does not rush to explain how that matching is demonstrated because Earth is still in this first movement learning how to be quiet enough for any delicate pattern to endure. Earth continues to cool in uneven ways, not as a smooth descent, but as a series of temporary plateaus, as if the planet keeps pausing to decide what solid is allowed to mean. A skin of crust forms and breaks again, stitched together by brief intervals of stability that do not last long enough to feel like permanence. Heat rises from below and impacts still arrive from above, and between them the surface becomes a place where matter changes phase as casually as weather. A scientifically accepted process remains central in this interval. Volatile compounds escape from the interior through vigorous volcanism, building a secondary atmosphere after any earlier gases are stripped away by impacts or lost to space. This outgassing supplies water vapor, carbon dioxide, nitrogen, and a spectrum of sulfur and carbon-bearing gases, a chemical breath that is neither gentle nor optional. Only takes a few million years for a planet to rebuild an atmosphere, and then it spends far longer pretending it never risked losing it. The air is not thin in the human sense, but it is thin in the sense that it is not yet regulated by oceans biology or long-lived continental weathering. It is an atmosphere that fluctuates, sometimes heavier with vapour when the surface is hotter, sometimes clearer when condensation steals water back down into basins. Above it, the boundary with space is not a sharp wall, but a gradient of decreasing density, a fading into near vacuum that still remains full of activity. In that upper reach, solar radiation breaks molecules apart and lighter atoms can escape, especially hydrogen, the smallest and least patient passenger. This is one of the quiet engines of long-term change. Hydrogen escapes to space over geologic time, and its loss can slowly alter the oxidation state of the atmosphere and surface. A planet, even without life, can drift chemically simply by being warm and exposed to starlight. Only takes an open sky for chemistry to become a slow leak. At the same time, the universe's most famous emptiness is never truly empty. Vacuum in quantum field theory is not a blank stage, but the lowest energy state of fields that fill all of space. Even in that ground state, fluctuations occur, temporary changes in energy that arise from the structure of the theory and the uncertainty principle. They're not free energy in the practical sense, and they do not allow nature to cheat accounting, yet they are real in measurable consequences, such as the Casimir effect, where two close uncharged conducting plates experience an attractive force due to altered vacuum modes between them. A scientifically accepted fact settles here. Without drama, quantum vacuum fluctuations and zero-point energy are not metaphors, but features that influence observable phenomena. Only takes two metal plates in a careful setup for nothing to start pushing. Earth's early sky then becomes a layered lesson in what counts as empty. Near the ground, dense vapour and ash carry heat and chemical potential. Higher up, the air thins and sunlight arrives less filtered. Beyond that, space begins, yet even there fields remain, fluctuations remain, and radiation and particles flow through. The planet sits in an environment that is never truly still. A lesser-known, real-world detail drifts quietly into view: the exosphere. The outermost layer of an atmosphere can extend far enough that atoms are on trajectories more like satellites than gas molecules, and in modern times Earth's exosphere includes a faint cloud of hydrogen called the geocorona that extends tens of thousands of kilometres. In the Hadean the details differ, but the principle holds: an atmosphere does not end, it fades. Only takes a gradient for borders to become uncertain. Quantum entanglement belongs to this same universe of blurred boundaries. It arises when two systems share a single description that cannot be decomposed into independent parts. The word share is precise. It means the combined system has a state that is not equal to a simple product of each subsystem's state. When measurement occurs on one part, the outcomes are correlated with measurement outcomes on the other part in ways that exceed what classical probability can explain under the assumption of local hidden variables. The key point remains: calm and technical entanglement does not transmit usable information faster than light, because the individual outcomes remain random. It is the pattern of correlations revealed only when results are compared that carries the signature. Only takes a careful comparison afterward for the strangeness to appear, and by then the speed limit has already been obeyed. The early Earth does not provide conditions to preserve delicate quantum correlations at large scales. Heat and constant interaction cause decoherence quickly. Yet the existence of decoherence does not eliminate the underlying quantum structure. It explains why everyday systems appear classical. This is where the vacuum's refusal to be empty becomes an understated companion concept. Even when a system appears ordinary, the underlying description may still involve quantum fields and their fluctuations with classical behavior, emerging as a statistical, environmentally enforced limit. Earth's atmosphere, thick with collisions, is a theatre for this emergence. Molecules exchange energy, photons scatter, and any phase-sensitive coherence between microscopic alternatives washes out almost instantly. Only takes a warm gas for quantum subtlety to become thoroughly averaged. A soft irony arrives in that washing out. Quantum theory is the foundation of chemistry, yet the conditions that make chemistry vigorous, warmth, density, constant collision, also destroy the fragile signatures of quantum coherence that make entanglement feel surprising in the laboratory. Another irony follows: dry and slow vacuum fluctuations are real enough to push plates together, yet they remain invisible to the senses and irrelevant to daily survival. So the most persistent activity in emptiness is ignored, while dust and weather receive the credit for being dynamic. A third irony rests beside the planet's outgassing Earth. Builds an atmosphere by releasing gases from within, while many later experiments meant to demonstrate entanglement work best by removing gases and pumping out air, as if nature's most delicate connections require engineers to imitate space. As Earth's surface temperature drops, water begins to shift from vapor toward liquid. The formation of oceans is not a single moment but a threshold crossed and recrossed. When atmospheric pressure and temperature allow condensation, rain falls in volumes that are difficult to imagine in modern terms. Warm precipitation over hot rock, an early hydrologic cycle that is less about seasons and more about phase change under a cooling sky. Yet this remains an area with genuine uncertainty. How quickly do oceans become stable after the planet cools, and how often do major impacts return water to vapor? How much water is delivered by impacts versus retained from Earth's formation? And how much is lost to space through hydrogen escape? The evidence is incomplete, and the models depend on assumptions about early bombardment rates, outgassing intensity, and the evolving luminosity of the Sun. The ocean, one of Earth's defining features, begins as a question with multiple plausible pathways. The vacuum, too, holds questions that remain unresolved in a deeper sense. Quantum field theory describes vacuum energy, yet its relationship to gravity and the expansion of the universe remains one of physics' most stubborn mismatches, often discussed under the problem of the cosmological constant. Observations show an accelerated expansion consistent with a small positive vacuum energy density, while naive calculations of quantum vacuum contributions yield values wildly larger, requiring cancellations that feel unnatural. This is a quiet scientific mystery that does not threaten the success of quantum theory in laboratories, but exposes an incomplete union between quantum physics and gravitation. The story holds it gently without trying to finish it. The vacuum is active, its activity is measurable, and its accounting with space-time remains unsettled. Only takes the universe itself as an experiment to reveal where theory still strains. In the Hadean to early Archean transition, Earth's interior and surface exchange matter continuously. Volcanic plumes feed the atmosphere. Rainfall and chemical weathering feed the crust. Subduction and recycling, if present in some form, pull material back down. The planet behaves like a slow engine of mixing, though the mixing is uneven and local, constrained by temperature, viscosity, and the still-forming architecture of tectonics. A gentle modern analogy can sit here without forcing itself. The planet's outgassing resembles a planetary exhale that never quite ends, not a single breath, but a long, repetitive release that slowly alters what the surface can become. The analogy remains limited, a small bridge, and then it dissolves back into stone and gas. Entanglement, meanwhile, remains a connection defined not by physical tethering, but by shared description. That shared description seems to challenge the idea that systems carry their properties independently before measurement, and it seems to challenge the comfort of locality, even while it respects relativistic causality. The atmosphere's fading boundary into space becomes a natural motif. Borders are not as firm as they look. Earth's early air thins into a region where molecules behave more like solitary travellers, and beyond that the vacuum still carries fields. In the quantum realm, the boundary between one system and two systems is also less firm than it appears because the mathematics can bind parts into a whole that does not reduce cleanly. Only takes a definition of the system for the world to decide whether it will look separable. The section lingers on that shared condition without insisting on wonder. Earth's surface continues its slow cooling, its atmosphere continues its chemical churn, and space continues to be full of not quite nothing. The universe offers a vacuum that refuses to be empty, and a planet that refuses to be stable quickly, and the two sit together under the same physics without needing to acknowledge each other. The connection that breaks common expectations is introduced in the gentlest way, not as a spectacle, but as a feature of how nature permits correlations while forbidding shortcuts. Only takes a long time for humans to notice, and far longer for Earth to become quiet enough to host the noticing. Earth's surface settles into longer intervals of crust that survives not because violence ends, but because the balance slowly shifts. The rate of the largest impacts declines, and the planet's own heat output begins to ease, and between those changes the idea of persistent ground becomes less temporary. The Archean eon unfolds still impossibly distant, and the surface is now a mosaic of hot ocean volcanic islands and early crustal fragments that form and reform along the edges of rising and sinking rock. A scientifically accepted process guides the scene. Partial melting. In the mantle produces magmas that rise cool and crystallize, building new crust, while leaving behind chemically altered mantle residues. Over time, this differentiation helps create the compositional diversity of Earth's crust and mantle, and it lays groundwork for later plate tectonics. Only takes a few 100 million years for one kind of rock to become many, and then the planet spends the rest of its life sorting them again. The oceans, once intermittent, become more stable. They are warmer than modern oceans, and their chemistry is different, iron-rich in many regions with little free oxygen, and with dissolved minerals supplied by intense hydrothermal circulation. At mid-ocean ridges and volcanic seamounts, Seawater percolates through hot rock, reacts and emerges, altered, carrying heat and chemicals back into the ocean. These hydrothermal systems are a real and central feature of early Earth. They move energy, they alter crust, and they shape ocean chemistry. A poetic detail hides inside this circulation. Vents and fractures turn the seafloor into a slow-breathing fabric, inhaling cold water and exhaling warmed mineral-laden fluid, a continuous exchange that does not require seasons. Only takes a crack in basalt for an entire ocean to begin circulating through the planet's skin. Above, the sky remains hazy, the sun still fainter than today, and the atmosphere still dominated by nitrogen and carbon dioxide with other volcanic gases mixed in. Methane may be present in significant amounts depending on early microbial activity and atmospheric chemistry, and it can act as a greenhouse gas, helping maintain liquid oceans under a weaker sun. The exact balance remains uncertain, tied to poorly constrained fluxes and to the details of photochemistry under early ultraviolet radiation. This uncertainty is quiet and persistent. The early climate must stay warm enough for liquid water, yet models require greenhouse support and the sources and sinks are complex. Only takes a few missing parameters for the early Earth to look frozen on paper while remaining wet in rock evidence. In the same universe, in the same era, particles learn to pair in ways that are less like bonds and more like shared states. Entanglement becomes clearer as a concept when it is linked to preparation. Two particles interact or are created in a single process, and the combined result is a state where certain properties are not independently defined. Consider spin, a quantum property that behaves like angular momentum, but does not map neatly onto classical spinning objects. In an entangled pair of spin 1/2 particles prepared in a singlet state, measurements of spin along the same axis yield opposite results, yet neither particle carries a pre-assigned instruction set that can account for the full range of correlations across different measurement settings. The scientifically accepted point remains simple and hard quantum correlations can violate inequalities that any local hidden variable theory must satisfy. Only takes one careful arrangement of measurements for classical intuition to begin losing its footing. The section stays slow with what pairing means here. It is not romance, it is not telepathy, it is not a wire, it is a shared mathematical object. The combined state is the thing that is well defined, and the individual parts are in that sense incomplete descriptions until measurement. This is less a philosophy than a formalism supported by experiment. The pairing is also fragile. If the particles interact with an uncontrolled environment, the entanglement degrades and the system behaves more classically. That fragility echoes the early ocean's chemical sensitivity. Both are systems where interaction changes what is possible. Only takes a few extra collisions to turn a delicate correlation into ordinary noise. On the Archean seafloor, minerals precipitate from vent fluids, creating chimneys and layered deposits. Iron and silica can form banded structures that later become banded iron formations, though many of the most famous banded iron formations accumulate later as oxygen begins to rise and react with dissolved iron. Even so, the Archean Ocean already holds vast dissolved iron, and its eventual fate is written into chemistry waiting for a trigger. A lesser-known real-world detail fits here with restraint. Some ancient hydrothermal deposits preserve microscopic textures that record flow patterns and mineral growth at a scale where the rock looks woven as if the chemistry once had a grain. This is not decoration. It is a record of conditions, temperature gradients, fluid composition, and time. Only takes a slow precipitating mineral to leave behind a map of water movement in stone. Entanglement too leaves behind records, though not in stone. It leaves statistical patterns across many repeated trials. A single entangled pair does not announce itself. It looks like randomness when measured alone. The signature appears only when outcomes from both sides are compared and sorted according to the chosen measurement settings. This is an irony that remains almost gentle. The phenomenon that most challenges classical expectations hides inside data that looks like noise until it is carefully aligned and counted. Only takes thousands or millions of trials to reveal what the universe is doing on every trial. Another irony follows the experimenter's choices of measurement settings matter for the correlations observed, yet those choices cannot be used to send messages through the entanglement. Nature allows dependence without allowing control. A third irony arrives quietly. Entanglement is often presented as if it is rare, yet in principle interactions naturally generate entanglement all the time, and what is rare is not its creation but its preservation in a clean isolated form. Earth's crust in this era carries its own rare preservations. Zircons and ancient gneisses, fragments of early crust, survive through cycles of melting and deformation. Some of the oldest known rocks, such as those in the Acasta gneiss complex, preserve ages exceeding 4 billion years, though they are transformed and reworked. They are not pristine snapshots, they are palimpsests rewritten by heat and pressure. The uncertainty remains: what did the earliest continents look like, and did plate tectonics operate in a modern style, or in a different episodic mode? Evidence suggests tectonic activity of some kind, but the timing of fully developed plate tectonics is debated. The planet may shift between stagnant lid behavior and more mobile regimes, or it may operate with smaller plates and more frequent recycling. The deep time record does not speak in simple sentences, only takes billions of years to make a clear story, and then the rocks still keep parts of it muffled. A gentle modern analogy can appear without insistence. Entanglement resembles a kind of bookkeeping in the universe, where the total remains orderly, even when the parts look unsettled, like a ledger that balances while individual entries seem random. The analogy stays small and then dissolves, because the universe does not require metaphors to function. In the ocean, the total salt content and heat budget follow constraints, yet local eddies and plumes look chaotic. In the quantum lab, total correlations follow precise predictions, yet local outcomes look like coin flips. Only takes a statistical view to see the underlying structure. The story returns to the Archean water and stone, where the planet's chemical systems run without oxygen as a major free agent. Life may already exist, likely microbial, perhaps thriving in hydrothermal settings or shallow waters, but the earliest evidence remains debated and subtle. Carbon isotope signatures, microfossil-like structures, and stromatolite formations that may record microbial mats. The uncertainty here is profound but quiet. When exactly does life begin, and how should evidence be weighted in rocks that have been altered by billions of years of metamorphism? The story does not invent an answer. It simply holds the possibility as a background presence. A planet with liquid water and chemical gradients does not stay chemically idle for long, yet the specific path remains uncertain. Only takes one self-sustaining chemistry to start, and then it becomes difficult to prove long after the fact exactly how it began. Entanglement remains in this section as something that pairs without contact after separation, while Earth systems pair processes across distances through circulation and convection ocean currents, linking vents to surface waters, mantle convection, linking deep heat to surface volcanism. These are not the same kind of connection, and the story does not force them to match. It simply lets the motif sit nearby. The universe contains linkages that do not require closeness in the way common sense expects, whether through fluid circulation, gravitational attraction, or quantum correlation. Only takes a planet to reveal many kinds of connection, and one of them turns out to be mathematically stronger than classical locality can explain. Earth's interior becomes more clearly layered as time moves through the Archean. Not because layering is new, but because the planet's heat engine learned steadier rhythms. The metallic core is already gathered dense and deep, while the mantle above it remains in slow circulation, carrying heat upward and returning cooler material downward in a cycle measured in millions of years. A scientifically accepted process sits at the center of this steadiness convection. In the mantle transports heat and the cooling of the core, and the crystallization of an inner core over time help power a geodynamo generating a magnetic field that threads through the planet's space and influences how the atmosphere interacts with the solar wind. The timing and exact early strength remain debated, but the existence of a long-lived magnetic field is a defining planetary fact in Earth's later history. Only takes an ocean of liquid metal and a little rotation for a planet to turn itself into a magnet, and then it spends the rest of its life quietly insisting on invisible lines. The magnetic field is not a shield in the simple sense, yet it shapes the pathways of charged particles and helps limit direct atmospheric stripping by the solar wind. It creates a magnetosphere that stands off much of the flow, while still allowing complex interactions at the poles and in the magnetotail. The poetic detail is that this invisible structure is drawn in space like a stretched veil, compressed on the day side and pulled into a long night side tail, as if the planet trails a faint dynamic shadow made of fields rather than matter. Even in the Archean, under a more active young sun, Earth's magnetic environment is an evolving sculpture that is never seen directly by eyes, only inferred through effects and later measured with instruments, only takes a field to make space around a planet into a shaped place. Inside the mantle, differentiation continues. Melting is partial and selective, and it separates elements into different reservoirs. Incompatible elements, those that do not fit easily into the crystal structures of common mantle minerals, prefer the melt and migrate into the crust. Over time, this produces crust that is enriched in certain elements and mantle that is depleted. This separation is slow, persistent, and almost administrative in its consequences, building chemical differences that will matter for volcanism, for continental growth, and for the long carbon cycle. The irony is that a planet can write its most enduring features through processes that are neither dramatic nor fast, just repetitive sorting. Only takes a few percent melt again and again for the surface to become a distinct chemical province. The uncertainties remain real. When does modern-style plate tectonics begin with stable subduction zones and large coherent plates? Evidence suggests tectonic activity early, yet the mode may differ from today. Perhaps episodic, perhaps localized, perhaps operating with hotter, weaker lithosphere that behaves differently. Even the early magnetic field, often discussed as a necessary protection for atmosphere and water, carries open questions. How strong is it in the Archean? How stable? How often does it reverse? And what does that imply for atmospheric escape? The record is incomplete, and the planet's earliest pages are still written in faint ink. Only takes 4 billion years for evidence to become scarce, and then the arguments become careful by necessity. In the human era, a different kind of layering takes shape, made not of rock and metal, but of assumptions about how reality is allowed to behave. Classical intuition tends to grant locality events here should not immediately influence events far away, and realism properties should exist with definite values, whether or not anyone measures them. Quantum mechanics tolerates neither assumption in its strongest form, and entanglement forces the issue into the open. Bell's inequality becomes the formal hinge. It is not a single inequality, but a family of constraints that any local hidden variable theory must satisfy when describing correlations between measurement outcomes on separated systems. Quantum mechanics predicts and experiments observe violations of these constraints under appropriate conditions, This is the scientifically accepted fact that settles into place with quiet weight nature produces correlations that cannot be explained by any theory that is both local and endowed with predetermined hidden variables reproducing quantum statistics. Only takes a few angles of polarizers or a few settings of spin measurements to make an entire philosophical comfort zone feel underdefined. The story keeps the tone level and the machinery plain. Two particles are prepared in an entangled state. They travel apart. Measurements are performed with settings chosen independently at each side. Each individual result looks random. Yet when the paired results are compared, the joint statistics show a pattern stronger than any local hidden variable model can allow. The violation is not a trick and not a loophole of careless design. It is a repeated result across generations of experiments refined to close major loopholes involving detection efficiency and locality conditions using photons, atoms, and other systems. The important limit remains these correlations do not enable faster-than-light communication because the outcomes on either side alone remain unpredictable, and no setting choice can force a particular result at the distant side. Nature provides linkage without permitting direct control. Only takes a universe that likes constraints to make its strangest behavior follow rules more strict than intuition expects. A soft irony arrives. First, the experiments designed to show non-local correlations require immense local engineering, timing, alignment, calibration, shielding. So the proof that locality fails in a certain formal sense depends on relentless attention to the local details of apparatus. Another irony follows dry and sleepy. The results undermine the hope that quantum randomness is merely ignorance of hidden facts, yet they do so through statistics, meaning the argument against hidden variables comes from counting again and again, as if the universe cannot be persuaded except by paperwork. A third irony settles gently behind them. Entanglement is introduced as a dramatic connection, yet the connection refuses to behave like a usable channel, so it becomes a phenomenon that surprises and disappoints in the same breath, offering correlation while withholding messaging. Only takes a limit to turn a marvel into a disciplined rule. Earth's own inequalities are less formal but no less constraining. The interior can only cool so fast. The atmosphere can only lose so much before outgassing replenishes it. The ocean can only hold so much dissolved iron before chemistry forces precipitation once oxygen appears. These constraints shape the planet's path. In the Archean iron remains largely soluble in anoxic seawater, and the seafloor continues to host hydrothermal exchange building, chemical gradients that may support microbial metabolisms if life is present. The water above those vents is often darkened by fine particles and dissolved compounds, and the boundary between hot vent fluid and cold seawater forms shimmering interfaces where minerals precipitate in delicate turbulence. The poetic detail is that the seafloor, despite its heat and chemistry, can look like a slow snowfall of minerals, fine grains settling through water in the absence of waves accumulating layer by layer in quiet basins. Only takes still water for the planet to practice sedimentation as a form of memory. The scientific mystery in this section lingers at the border between entanglement and the large-scale world. Decoherence explains why macroscopic objects do not behave like entangled superpositions in everyday life. Yet it does not by itself resolve every question about measurement, especially across different interpretations of quantum mechanics. Why does measurement have the structure it does, and what precisely counts as a measurement in physical terms? Some frameworks treat collapse as fundamental, others treat it as emergent, others treat the wave function as information, rather than a physical object. Experiments continue to constrain possibilities, yet no single interpretation has become a settled consensus in the way the predictive machinery has. The mystery remains quiet because the predictions work regardless, but the explanatory picture stays plural. Only takes an extremely successful theory to leave deep questions untouched and still be correct about nearly everything it touches. A gentle modern analogy can sit here without overstaying Bell's inequality functions like a boundary line in a landscape marking what a certain class of theories can never cross, much as Earth's phase diagrams mark where water can never be liquid, or where rock must melt under pressure and temperature. The analogy is limited, but it helps the mind wrest constraints, define the shape of possibility. In the quantum case, the constraint is on local hidden variables. In the planetary case, the constraints are thermodynamic and chemical. Both are quiet fences. Nature rarely explains, simply enforces. Only takes a boundary to make a world feel orderly, even when its outcomes feel strange. The section remains with Earth's layered interior and the universe's layered assumptions. Core and mantle do not exchange freely, yet they remain coupled through heat flow and magnetic behavior. Entangled particles separate yet remain coupled through statistics that defy classical locality. Neither coupling is visible in the moment. Both are known through indirect signatures, magnetic measurements, and paleomagnetic records for Earth, coincidence counts and correlation curves for quantum experiments. The planet and the laboratory share a certain humility. The most important connections often announce themselves only after careful reconstruction. Only takes patience to see what is already happening. Light arrives before most other things feel stable, and it keeps arriving no matter what the surface decides to do with its heat. In the Archean world, sunlight falls through a thick changing atmosphere and reaches oceans that are still warm and chemically busy, and reaches basaltic plains and volcanic islands that lift themselves briefly above sea level before being broken down again. A scientifically accepted fact anchors the scene with quiet certainty. Photons carry energy in discrete quanta, and when light interacts with matter, it does so through quantized transitions. Electrons in atoms and molecules absorb and emit photons at specific energies, shaping how atmospheres heat, how minerals reflect, and how oceans absorb warmth. The early sun's spectrum and intensity differ from today, yet the same quantized rules govern every absorption line and every scattering event, whether in a laboratory vacuum chamber or in a haze over a 4-billion-year-old sea. Only takes a single photon to be both a particle-like packet and a wave-like spread, and then it spends the rest of physics class refusing to pick one description for comfort. Earth's surface offers a matching stubbornness. It is neither fully liquid nor fully solid, neither fully calm nor fully catastrophic, and it accepts light as an input without offering a clean output. Over basalt that cools in rippled sheets, sunlight meets crystals forming in place plagioclase, pyroxene, olivine, each with electronic structures that determine how light is absorbed, scattered and re-emitted as heat. The poetic detail is small and real fresh. Basalt can develop a thin glassy skin where lava quenches quickly against air or water, and that skin can glitter faintly in low angles of light, not with brightness, but with a subdued sheen that records rapid cooling in a frozen texture. Only takes a surface to cool too fast for perfect crystals, and it leaves behind glass that remembers the heat it cannot hold. In the sky above, aerosols and gas molecules scatter short wavelengths, but the composition of the air and the presence of haze complicate the colour. The familiar blue is not guaranteed, and the light's path is longer and more filtered. The ocean surface receives the remainder and distributes it downward, where water absorbs strongly in parts of the spectrum, converting light into molecular motion and raising temperature in a slow planetary bookkeeping. This is the quiet engine of climate even in deep time. Radiative balance, the difference between incoming solar energy and outgoing infrared emission moderated by greenhouse gases that absorb and re-radiate heat. The faint young sun problem remains the steady puzzle behind the calm description. Evidence indicates liquid water too early, yet the sun is dimmer, so greenhouse warming must be stronger, or albedo lower, or heat transport and cloud physics must behave differently than simple models assume. The uncertainty is not decorative. It sits at the intersection of atmospheric composition, cloud behavior, and geological feedbacks, and it remains active research. Only takes a slightly different cloud microphysics assumption to turn an ocean into ice on paper, while rocks keep insisting the ocean stays liquid. Light does more than warm. It changes chemistry. In the upper atmosphere, ultraviolet photons can break molecular bonds, driving photochemistry that reshapes gases over time. In an oxygen-poor Archean sky, ultraviolet radiation penetrates more deeply than it does today because ozone is absent, yet other hazes such as organic aerosols produced from methane photochemistry can form and provide shielding. The details depend on methane abundance, on volcanic outgassing, on the presence and productivity of early microbes if they exist, and on the young sun's ultraviolet output. The planet's surface and its air engage in a long negotiation mediated by photons, where the terms shift as the chemistry shifts. Only takes a star's light to turn an atmosphere into an evolving reactor. This same mediator light becomes the instrument by which entanglement is most famously demonstrated, and it brings with it a parallel quietness. Photons are ideal messengers because they travel fast, interact weakly, and can be prepared in well-defined quantum states such as polarization. Polarization is the orientation of a light wave's oscillation, and in quantum terms it can be treated as a two-level system, a qubit with measurement outcomes that depend on the angle of a polarizer. When two photons are created together in certain nonlinear optical processes, such as spontaneous parametric down-conversion in a crystal, their polarizations can be entangled, meaning that neither photon has a definite polarization state on its own, yet their joint state produces correlations that violate Bell-type inequalities when measured at different settings. The accepted process is again plane entanglement is prepared through an interaction or joint creation, and measurement outcomes show correlations inconsistent with local hidden variable models. In this story, measurement remains an event that turns a spread of possibilities into a definite record, and light becomes the courier that carries that event from the microscopic to the macroscopic. The irony arrives first with the soft dryness. Photons are used to reveal non-classical correlations precisely because they are so good at not touching things, so the clearest demonstrations of interaction-dependent quantum phenomena are performed with the least interacting particles available. Another irony follows: the same light that enables precise quantum tests also floods Earth's early surface without restraint, driving photochemistry and heating oceans in a way that is indifferent to precision, as if the universe uses photons for both delicate bookkeeping and blunt thermal forcing without changing tools. A third irony settles gently behind them. Entanglement experiments often rely on counting single photons one by one to build statistical certainty, while Earth's climate responds to an unimaginable number of photons arriving every second, making the planet's most consequential radiative accounting depend on immense numbers that no one can count individually. Only takes one photon to be meaningful in a detector, and it takes uncountable photons to be meaningful in an ocean. Measurement in quantum mechanics is where the unfinished promises of light become visible. A photon in a superposition of polarization states does not carry a single predetermined answer to the question a polarizer asks. The outcome appears random, governed by probabilities set by the quantum state. Yet when two photons are entangled, their outcomes are linked beyond classical explanation. The promise is not that an outcome is known in advance, but that correlations are fixed by the shared state even when each single result remains unpredictable. This is why entanglement feels like a connection. It preserves a structure that survives separation, carried not as a signal, but as a constraint on joint outcomes. The story stays careful. Nothing travels faster than light in the sense of usable information, and causality remains intact. Yet the correlations refuse to be explained by local hidden instructions. Light carries this refusal across distance. In Earth's deep time, light carries a different kind of refusal. It keeps arriving even when the atmosphere changes, even when impacts darken the sky, even when haze thickens, even when oceans steam and later condense again. The surface can soften, harden, fracture, flood, and the photon stream continues steady in the long average with short-term variations. The lesser-known detail in this continuity is that even today the sun's energy output varies slightly with cycles and activity, and early in solar history the ultraviolet activity is higher even when total luminosity is lower, so the character of incoming light shifts as the star matures. Earth's early chemistry responds to that character, not merely to the total warmth. Only takes a change in ultraviolet flux to alter the balance between methane and haze, between transparency and shielding. The scientific mystery in this section remains near the heart of quantum theory. What precisely constitutes a measurement, and why does it yield one outcome rather than leaving the world in a superposition? Decoherence explains how interference becomes unobservable as systems entangle with their environments, effectively selecting stable pointer states. Yet the deeper interpretive question persists across competing frameworks. Some approaches treat collapse as fundamental, others treat it as apparent, arising from branching or from an informational update. And experiments continue to probe the boundary with larger systems seeking signatures that might distinguish models. The mystery remains quiet, not because it is small, but because the predictive rules are so reliable that daily work continues without resolving it. Only takes an unresolved foundation for an entire building to remain usable anyway. On Earth, the analog boundary is also unresolved in detail. The transition from a world dominated by rapid crust recycling and heavy outgassing into a world with more persistent continents and more stable climate feedbacks is gradual and partly hidden, and the exact timing and mechanisms remain debated. Light participates in that transition by driving weathering and photochemistry, by warming and shaping the hydrologic cycle, and by enabling much later the metabolism of organisms that use photons directly. For now, the section keeps the focus on light as a carrier of structure and uncertainty, a stream of quanta that warms basalt and water while also serving as the cleanest messenger of quantum correlation. In both contexts, light arrives with unfinished promises. It brings energy but leaves the details to matter. It brings probability but leaves outcomes to measurement. It brings continuity but allows Earth and physics to keep their deepest explanations partly unspoken. Heat does not merely move through Earth in this era, it insists on being part of every interaction, as if temperature is the planet's default language. The Archean world remains warm, the mantle remains active, the oceans remain chemically charged, and the atmosphere remains a shifting mixture shaped by outgassing sunlight and slow escape to space. Wherever matter touches matter, energy is exchanged, and those exchanges accumulate into what later eras call stability, even though in the moment it is only constant change. A scientifically accepted process sits at the center of this section, with quiet firmness. Decoherence occurs when a quantum system becomes entangled with its environment in uncontrolled ways, causing interference between different components of its state to become effectively unobservable, and making the system behave in practice as if it has chosen a definite classical outcome. Decoherence is not a mystical curtain, it is a consequence of interaction, and it happens extremely quickly for warm complex systems. Only takes a few stray collisions for a superposition to lose its delicate phase, and then the world resumes looking ordinary, as if nothing unusual had been permitted. Earth in the Archean is a masterclass in interaction. Water molecules collide in numbers too large to hold in mind. Dissolved ions exchange partners. Suspended particles settle and are lifted again. At hydrothermal vents, gradients sharpen and blur. Hot mineral-rich fluids meet colder seawater, producing precipitation and turbulence that are small in scale yet continuous in time. The seafloor hosts chemical microenvironments where temperature, acidity, and mineral surfaces create localized order, and then that order is dispersed by mixing. In such a setting, any fragile coherence is not merely threatened, it is overwhelmed by contact. The planet does not need to decide to be classical. Its density and warmth provide the decision continuously. Only takes an ocean to enforce a single outcome by relentless averaging. Yet the underlying quantum rules remain present everywhere, embedded in bond energies, mineral lattices, and reaction rates. Electrons occupy orbitals governed by quantum mechanics. Vibrations in crystal lattices are quantized as phonons. Even the thermal properties of rocks and water depend on quantum-level structures, though the behavior expressed at large scales looks smooth and classical. This is one of the quieter ironies of the universe. Quantum mechanics underlies nearly everything. Yet its most striking features, superposition and entanglement, are hardest to display in the very conditions where matter becomes interesting and reactive. Only takes the warmth that makes chemistry possible to erase the coherence that makes quantum behavior visibly strange. Another dry observation follows close behind. Laboratories spend effort removing the environment, cooling, isolating, shielding, while Earth's early surface spends its entire existence doing the opposite building. Environments with enthusiasm as if noise is a planetary hobby. A third irony arrives slowly. The same entanglement that makes decoherence happen is also what makes entanglement valuable in experiments. So the enemy of quantum delicacy is built out of the same correlations that researchers work to create only with the wrong partners and in the wrong places. Only takes the universe to be consistent for its tools to be double-edged. In physical terms, decoherence can be pictured as phase information leaking away into the environment. A quantum system's state involves amplitudes with relative phases, and those phases allow interference. When the system interacts with many environmental degrees of freedom, air molecules, photons, thermal vibrations, its alternatives become correlated with different environmental states. Because the environment is vast and uncontrolled, those environmental states become effectively distinguishable, and the system's interference terms vanish from any practical measurement. The system looks like a classical mixture rather than a coherent superposition, even though the combined system plus environment evolves under quantum rules. This point is precise and widely accepted. Decoherence explains why quantum behavior is not seen at macroscopic scales in ordinary conditions, and it does so without requiring a special boundary where quantum laws cease. Only takes a large enough environment to make the boundary feel real. Earth supplies environments in abundance. Consider the early atmosphere above the Archean Ocean, thick with water vapor, at times with carbon dioxide and nitrogen as major components, and with aerosols and haze depending on chemistry and sunlight. Photons scatter and are absorbed. Molecules rotate and vibrate, exchanging energy through collisions. The atmosphere behaves like a vast bath that can couple to any exposed surface, stealing and donating energy constantly. A lesser-known real-world detail fits here with the quiet patience of a mineral grain in modern air. Even at room temperature, the black-body radiation field contains a sea of infrared photons, and for many delicate quantum systems, these thermal photons are enough to drive rapid decoherence unless the system is cooled and shielded. In the Archean, temperatures are higher in many places, and thermal radiation is correspondingly more intense. The planet's own warmth becomes a background glow that is always present, a soft rain of photons that carries away information. only takes warmth to turn space around an object into an active participant. The story remains grounded in deep time as decoherence is introduced because Earth's history is full of transitions that look sudden only when compressed into a sentence. The cooling of a magma ocean into a crust, the condensation of water vapor into oceans, the shift from episodic impacts to steadier tectonic cycling, each change is an emergence of a new regime from countless interactions. Decoherence belongs to the same category of emergence. It is not a new law, but a new behavior that arises when systems become large, warm, and entangled with their surroundings in untracked ways. The theme repeats softly without repetition of facts, borders fade, and the world becomes definite not by decree but by contact. Only takes constant touching for ambiguity to become unlivable. A quiet scientific mystery remains, and it is carefully kept distinct from what decoherence does explain. Decoherence explains the disappearance of observable interference and the practical emergence of classicality, but it does not alone answer why a single definite outcome is experienced or recorded in any given trial, rather than all outcomes remaining equally real in the combined state. Different interpretations of quantum mechanics offer different accounts, collapse as physical collapse, as informational branching, as literal hidden variables constrained in particular ways, yet no interpretation has achieved the kind of consensus that the mathematical predictions have. Experiments continue to push coherence to larger masses and longer times, and to test whether quantum behavior persists as expected. But the question of what measurement is remains a place where language becomes careful and modest. Only takes a theory that works too well for its unanswered questions to stand out more clearly. Earth's own unanswered questions sit nearby, in mood if not in category. In the Archean, the exact pathways by which early continents grow remain debated, as does the timing of stable plate boundaries and long-lived subduction. The rock record is incomplete and heavily altered. Isotopic systems and mineral inclusions provide clues, yet they leave room for multiple models. The planet's earliest measurements are locked in minerals that survive, and the outcome is always partial. Only takes billions of years of metamorphism to decohere geology's own delicate evidence. A gentle modern analogy can appear and then fade. Decoherence resembles a whispered sentence spoken into a crowded room where the words are technically still present as vibrations in air, yet they are quickly drowned in other sounds, making the original pattern unrecoverable in practice. The analogy remains restrained because the physics is already clear, and the section does not seek drama. Earth's Archean surface is that crowded room full of collisions and exchanges, and quantum coherence is that whispered pattern that survives only when the room is emptied and cooled. Only takes silence to let a faint structure persist. In the laboratory, the struggle against decoherence becomes a defining engineering challenge. Vacuum chambers, cryogenic cooling, electromagnetic shielding, error correction codes, and careful timing are all ways to reduce unwanted coupling or to repair its effects. In the Archean world, the struggle does not exist as a struggle. The environment is not something to eliminate, but something that builds the planet. Ocean circulation distributes heat, chemical weathering begins to link atmosphere and crust, and hydrothermal systems keep the seafloor reactive. These processes are the opposite of isolation, and they are the conditions that make Earth Earth. The section lingers on this without forcing a moral of the same universe that permits coherence, also prefers in most natural settings to erase it quickly. And the same planet that will one day host quantum experiments spends its youth being too loud for them. Only takes a few billion years for Earth to become calm enough for delicate correlations to be protected, and then quietly the protection becomes part of the story the planet tells about itself. Water becomes a kind of punctuation in Earth's early history, marking where heat can be carried away, where chemistry can proceed, and where rock can be transformed without the violence of impact. By the time the Archean settles into its longer middle, the oceans are not merely present. They are active agents, circulating through crust, dissolving minerals, precipitating new ones, and exchanging gases with an atmosphere that remains oxygen-poor. A scientifically accepted fact sets the foundation without haste. Seawater interacts with basaltic crust through hydrothermal circulation, altering minerals, exchanging elements, and transferring heat. And this process is fundamental to the chemistry of oceans and to the long-term cycling of elements on Earth. The early ocean is warmer and chemically distinct from the modern one, but it is still governed by the same physical truths of fluid flow, heat exchange, and reaction kinetics. Only takes a planet with water and heat to create an ocean that never truly stops moving. The seafloor in this era is not an inert boundary, but a porous interface cracked and fractured by thermal contraction, tectonic stress, and the settling of new volcanic layers. Through those cracks, seawater descends, warms, reacts, and rises, carrying with it dissolved metals and altered chemistry. In the dark near vents, iron can be abundant sulfur. Species can dominate, and pH can shift sharply across centimeters. The poetic detail remains grounded in some hydrothermal settings. Mineral chimneys grow by accretion layer upon layer, as if the seafloor is slowly building its own fragile architecture out of the water's dissolved load, and those chimneys can collapse and regrow, leaving behind piles of broken mineral ribs. Only takes a gradient and time for stone to assemble itself underwater without anyone watching. The early ocean is also by its nature a generator of noise in the quantum sense. Each molecule is in constant thermal motion, each collision exchanging momentum and energy. Any microscopic system immersed in such a bath cannot remain isolated. This is part of why the ocean becomes a natural image for what decoherence feels like: a continuous, restless environment that absorbs information and spreads it until specific patterns cannot be recovered. Yet the section is not a metaphor. It is an alignment of behaviors under the same physics. The ocean's motion is classical in expression, but it is underwritten by quantum interactions in the bonds and excitations of water and dissolved ions. Only takes an uncountable number of quantum events to produce a single smooth current. Into this restless water, the idea of noise becomes both planetary and experimental. In laboratories, noise is a threat to quantum coherence and entanglement. It includes thermal vibrations, stray electromagnetic fields, and uncontrolled interactions with the environment. In the Archean ocean, noise is simply life of the system, the necessary agitation that enables mixing and reaction. A quiet irony arrives. First, the conditions that make Earth's oceans chemically rich heat dissolved. Ions' constant collision are precisely the conditions that make long-lived quantum entanglement difficult to maintain. So the planet's most habitability-relevant medium is also, from a quantum engineering perspective, a hostile environment. Another irony follows, dry and slow. The ocean is often imagined as calm when viewed from above, yet at the molecular scale it is never calm at all, meaning Earth's most soothing-looking surface hides its most relentless agitation. A third irony settles behind them. Humans later learned to cool systems toward absolute zero to protect quantum coherence, while Earth's earliest oceans form at temperatures far from that ideal, and still they become the cradle for much of what later matters on the surface. Only takes a few hundred degrees of difference to turn ideal into impossible, and nature proceeds anyway. The atmosphere above the ocean remains thick with carbon dioxide and nitrogen, and it may contain methane in significant amounts depending on sources and sinks. In an anoxic world, methane can persist longer, yet ultraviolet light can break it down, forming organic hazes under certain conditions. Those hazes can reflect sunlight and cool the planet while also providing ultraviolet shielding, adding complexity to the early climate. The uncertainty remains steady and real. How much methane is present? How reflective are haze layers? How do clouds behave under different aerosol burdens? And what does that mean for surface temperature? The faint young sun problem remains a background puzzle, not because it is unsolved in all respects, but because it depends on coupled systems that are hard to reconstruct from deep-time evidence. Only takes a single feedback loop to make a climate stable, and it takes many feedback loops to make its reconstruction uncertain. In the quantum realm, noise is not merely an inconvenience, it shapes what entanglement can be. Entanglement is a resource in quantum information precisely because it enables tasks impossible with classical correlations alone. Yet it is also a fragile resource degraded by interaction with uncontrolled environments. In practical terms, entangled states become mixed states as noise acts, reducing correlation strength and eventually destroying the ability to violate Bell inequalities or to perform high-fidelity quantum protocols. This is a scientifically accepted process. Environmental decoherence and noise reduce entanglement, and preserving it requires isolation, error correction, or both. Only takes a warm photon bath, a vibrating lattice, or a drifting field to turn a pure entangled state into something ordinary. The section keeps the ocean close as a real-world place where gradients persist despite noise. At hydrothermal vents, steep chemical and thermal gradients are maintained because energy and material are continuously supplied. This is a kind of steady-state order, not fragile coherence, but it shows how structured patterns can endure in noisy environments when they are driven. A gentle modern analogy can appear here without insisting. A hydrothermal system is like a planetary exhale that never stops, at one point continuously renewing its chemistry, so patterns remain even though every molecule is replaced. The analogy remains limited, and then the description returns to what is measured temperature, differences, mineral assemblages, isotopic signatures. Only takes constant supply for a structure to persist without being static. A lesser-known, real-world detail fits this driven persistence. Some modern vent systems produce mineral deposits rich in sulfides and carbonates, and their microstructures can record fluid pathways in fine laminations and crystal habits, offering a kind of fossilized flow. In Archean analogues preserved in ancient greenstone belts, geologists look for altered basalts, cherts, and sulfide deposits that suggest ancient hydrothermal activity, though the record is often overprinted by metamorphism. The details are difficult, and interpretation requires caution because later heating and deformation can mimic or erase original textures. This is one of Earth history's quiet uncertainties. The planet's most chemically significant early environments are often the hardest to read because they occur in settings later subjected to high temperature and pressure. Only takes a few billion years of tectonic recycling to make the earliest seafloor almost entirely disappear. The scientific mystery in this section remains at a different boundary. If entanglement is a basic feature of quantum theory, and if noise and decoherence are ubiquitous, how does the classical world emerge so robustly? And could there be natural systems that exploit quantum coherence even in warm conditions? In biology and chemistry, there are ongoing studies of quantum effects in certain processes, such as excitonic coherence in photosynthetic complexes or tunneling in enzymes. Yet the extent and functional relevance remain active. Research, with careful debate about interpretation and timescales. The story does not claim more than the evidence warrants. It holds the question gently. Nature can sometimes maintain quantum coherence briefly in complex settings, but the line between meaningful quantum advantage and transient coherence remains under investigation. Only takes a few femtoseconds of coherence to be interesting, and it takes a great deal of evidence to show it matters. Earth's Archean oceans continue indifferent to these later questions. but they do provide the raw conditions that make the questions unavoidable. A planet with water and heat creates gradients, and gradients create opportunities for ordered processes amid noise. At the same time, the ocean's restless molecular motion is a constant reminder of why macroscopic entanglement is not an everyday sight. The connection that breaks physics does not break it by violating laws. It breaks it by violating expectations. And those expectations are built from a world where oceans, atmospheres, and rocks are always interacting, always decohering, always converting delicate possibilities into blunt outcomes. Only takes a warm sea to keep the universe's strangest correlations hidden until someone learns how to drain the room of noise. Even in a world saturated with interaction, the universe continues to allow small pockets of quiet order, not as exceptions to physics, but as particular arrangements of matter and energy where certain patterns persist longer than expected. Earth's Archean surface, for all its heat and chemical flux, contains such pockets in the most literal sense. Mineral lattices that hold their structure protected spaces within crystals and stable temperature niches where reactions proceed in repeatable ways. A scientifically accepted fact provides the framing quantum coherence can persist for measurable times in systems that are sufficiently isolated from environmental disturbances, and in condensed matter it can appear in collective forms such as superconductivity and superfluidity, where many particles share a coherent quantum state. These phenomena require specific conditions, often very low temperatures, and they demonstrate that coherence is not limited to single particles. It can become a property of a macroscopic phase of matter. Only takes the right constraints for a vast number of electrons to behave as if they share a single quiet rule. Earth in the Archean is not a natural refrigerator in the way a cryostat is, yet it still hosts conditions that approximate isolation in narrower local ways. Deep in the ocean, certain layers are thermally buffered. Within minerals, defects and inclusions can trap fluids or gases. In the mantle, pressure and composition can stabilize phases that are inaccessible at the surface. None of these create superconductors in the early ocean, and the story does not pretend they do. Instead, they serve as a sober reminder that environment is not a monolith. It is a spectrum of couplings. Some places couple strongly, some weakly, and the persistence of a pattern depends on the coupling strength and on the timescale of interest. Only takes a small reduction in disturbance to turn instant disappearance into a measurable duration. In quantum information, this is the basic hope that coherence can be extended long enough to be used. This section keeps that hope close to Earth's own slow stabilizations. As continents begin to grow and survive longer, the planet develops more persistent chemical gradients between land, sea, and air. Weathering begins to act as a long-term regulator. Carbon dioxide dissolves in rainwater, reacts with silicate rocks, and eventually ends up locked into carbonate minerals or carried to the ocean where it can be subducted and returned through volcanism. The exact early form of this carbon-silicate cycle is debated, especially given different tectonic regimes, but the underlying process, chemical weathering, consuming carbon dioxide and influencing climate over long timescales, is accepted as a central stabilizing feedback on Earth. Only takes a slow chemical sink to turn climate into something that can hover rather than drift endlessly. A poetic detail sits within this slow feedback. Rain falling on fresh volcanic rock can be unusually reactive because newly formed basalt offers abundant surfaces and unstable minerals eager to transform, so a landscape built of young lava can act like a chemical sponge quietly pulling gases out of the sky. Only takes wet stone for an atmosphere to be edited by contact. The scientific mystery remains as it has in earlier sections, in the exact timing and style of early plate tectonics and in the detailed composition of the Archean atmosphere. but here the uncertainty is allowed to coexist with a clearer sense of long-term regulation. Earth is not stable in the human sense yet. It becomes stable enough to keep oceans liquid and to allow persistent surface environments across hundreds of millions of years. The planet's stillness is achieved not by stopping motion, but by balancing opposing flows. Only takes a feedback loop to produce calm that is built from continual change. In quantum physics, the analogous calm is achieved by balancing isolation and control. Coherence is extended by reducing interactions with uncontrolled environments and by using error correction and clever encoding to spread information across many physical systems so that local disturbances do not immediately destroy it. The concept of an island of coherence appears naturally here not as a metaphor but as a technical goal, a region of state space where quantum information remains accessible despite surrounding noise. In practice, such islands can be found in trapped ions, superconducting circuits at millikelvin temperatures, neutral atoms in optical lattices, and certain solid-state defects like nitrogen vacancy centers in diamond. The accepted fact remains, coherence dams vary widely across physical platforms, and extending them is a central challenge in quantum technology. Only takes a slightly cleaner environment to turn coherence from microseconds to milliseconds, and then people learn to ask for seconds. A soft irony arrives. First, the most promising islands of quantum coherence often require conditions far removed from the everyday world. Ultra-high vacuum extreme cold and meticulous shielding, so the natural behavior of matter must be carefully suppressed to reveal a deeper natural behavior. Another irony follows Earth's long-term stability is achieved through openness through exchange between atmosphere, ocean, crust, and mantle, while quantum coherence is achieved through closure through limiting exchange, so the planet becomes calm by touching everything and the qubit becomes calm by touching almost nothing. A third irony settles gently behind them. Islands in geology are often born from volcanism and then erased by erosion and subsidence, while islands of coherence in physics are engineered to resist erosion by noise, as if the two kinds of islands live under opposite rules, yet share the same longing to persist. Only takes time for every island to be tested by its surrounding medium. The section stays with Earth's quiet mineral places. In certain Archean terrains preserved today, ancient rocks are altered into greenstone belts, assemblages of metamorphosed volcanic and sedimentary rocks that preserve hints of early oceanic crust and island arcs, though the interpretations remain complex. Within these belts, geologists find pillow basalts, rounded bulbous forms created when lava erupts underwater and cools, rapidly forming a skin that inflates and breaks as new lava pushes outward. This is a lesser-known detail that is also deeply physical. Each pillow records rapid quenching fluid dynamics and the boundary conditions of lava. Meeting seawater and the glassy rinds can preserve chemical signatures of the interaction. Only takes lava meeting water for rock to take on a shape that looks almost biological, though it is only physics and cooling. The scientific mystery here is the same one that shadows the earliest ocean story. How representative are these preserved fragments, and how much of early Earth's seafloor behavior is missing because it has been recycled or transformed beyond recognition? The planet's earliest oceans cover most of the surface, yet the surviving rocks are scarce and altered, making the sampling bias severe. Only takes plate recycling to erase an archive, and then the few surviving pages carry an outsized burden. Quantum coherence has its own sampling challenge. Experiments reveal coherence by measuring interference patterns, by observing oscillations, by performing tomography of quantum states. Yet the measurement process itself can disturb the system, and the environment can mimic or obscure certain signatures. Engineers and physicists learn to infer coherence from indirect indicators, much as geologists infer early conditions from mineral isotopes and textures. The analogy remains gentle and limited. Both fields depend on reconstructing invisible processes from partial traces. Only takes a system to hide its inner state for science to become an art of inference. A quiet scientific uncertainty remains in the quantum story at this point, what ultimately sets the limits of coherence in complex systems. Some limits are practical imperfect shielding, material defects, uncontrolled vibrations, while others are fundamental in the sense that any coupling to a thermal environment introduces noise. There are ongoing efforts to understand and mitigate decoherence through better materials, better designs, and more robust error correction. Yet the scaling to large, fault-tolerant systems remains an open frontier. The uncertainty is not whether coherence exists, but how far it can be extended in practice without prohibitive overhead. Only takes a few extra error channels to turn a clean theory into a difficult engineering problem. Earth's Archean stability continues to deepen in parallel without needing laboratories. Oceans persist, continental fragments grow, weathering and volcanism exchange carbon. The atmosphere remains reducing compared to the modern one. The magnetosphere shapes particle flux. These are not islands of coherence, yet they are islands of persistence in their own domain patterns that endure despite constant perturbation. The section leaves a calm impression that the universe allows persistence in many forms, whether it is a mineral lattice that survives billions of years, a feedback loop that stabilizes climate, or a quantum state protected long enough to be used as a resource. Each persistence is hard-won, not by struggle but by conditions. Only takes the right conditions for a fragile pattern to last longer than expected. Time on early Earth does not feel like a line. It feels like a slow accumulation of irreversibilities. Heat leaks outward and does not return in the same organized way. Minerals crystallize and once formed do not spontaneously uncrystallize without new inputs of energy and pressure. Water circulates through rock and the rock is altered, and the alterations persist until they are overwritten by metamorphism or melting. The Archean planet keeps moving, yet each movement leaves traces that cannot be perfectly undone, and those traces are what make geology readable at all. A scientifically accepted fact sets the anchor. The second law of thermodynamics states that in an isolated system, entropy tends to increase, and while Earth is not isolated, it receives energy from the Sun and radiates energy to space. The local irreversibilities that create entropy still govern the direction of natural processes from heat flow to chemical reactions. Only takes a temperature gradient for entropy production to begin, and Earth provides gradients everywhere. This directionality, the so-called arrow of time, feels obvious in daily life, yet it sits uneasily beside the time-symmetric equations that describe many fundamental interactions. In classical mechanics, and even in much of quantum mechanics, the underlying equations allow time reversal in principle, yet the world experienced at large scales does not. The early Earth becomes a calm stage on which this mismatch is visible without needing to be explained with urgency. Magma cools, impacts dissipate energy into heat. The ocean spreads and mixes. None of it runs backward. Only takes a planet to demonstrate irreversibility with patient repetition. A poetic detail rests in the way heat escapes in volcanic regions. Night can reveal dull glows along fissures, and even without a human observer, thermal radiation carries information away into space as infrared photons, a continual silent broadcast of the planet's internal energy. Those photons do not return. They carry away energy and, in a sense, the record of the planet's temperature distribution at that moment. Only takes an open sky for a planet to lose heat by shining faintly in wavelengths no eyes are built to see. The arrow of time is also embedded in chemistry. In an anoxic Archean ocean, iron remains soluble and vast quantities can circulate without precipitating as rust-coloured minerals. When oxygen later becomes available, iron oxidizes and precipitates, producing banded iron formations in the Proterozoic. In the Archean, this future is not yet realized, but the chemical setup already contains an irreversible trap. Once oxygen appears in sufficient amounts, it will react with reduced species and be consumed, leaving behind mineral records that cannot be unmade without reversing oxidation. Only takes a new reactant to make an entire ocean's chemistry move in one direction. In the quantum story time's arrow appears in a more delicate way. The fundamental evolution of an isolated quantum state under the Schrödinger equation is unitary and reversible, yet measurement and decoherence introduce an effective irreversibility. When a system becomes entangled with a large environment, the information about relative phases disperses into degrees of freedom that are practically inaccessible, making the original coherent state effectively unrecoverable. This is not a violation of the underlying reversible evolution of the total system, but it is a practical irreversibility for the subsystem. The scientifically accepted point is that decoherence provides a mechanism for the emergence of classical irreversibility from quantum dynamics when environments are large and uncontrolled. Only takes a sufficiently complex environment for reversibility to become a mathematical possibility and a physical impossibility. Earth is such an environment by default. Yet entanglement complicates the arrow of time in a subtler way, because it can encode correlations that are not local and not separable. In thermodynamics, entropy is often linked to missing information about microstates. In quantum systems, entanglement entropy becomes a measure of how much a subsystem is correlated with another. This allows a precise modern language for irreversibility as systems interact, entanglement spreads, and subsystems become more mixed, more uncertain on their own, even as the total system remains in a pure state. The arrow of time can be traced in many cases by the growth and spread of entanglement. This is a real and active area of research in quantum thermodynamics and many-body physics, though the basic connection between entanglement and the emergence of thermal behavior has strong support. Only takes interaction for entanglement to become the bookkeeping of irreversibility. A soft irony arrives. First time's arrow is usually taught with macroscopic examples: spilled ink, cooling coffee. Yet at a deep level, the arrow is often about the spreading of correlations, the very thing entanglement describes most sharply. Meaning the strangest quantum concept becomes a tool to explain the most familiar experience. Another irony follows dry and slow. The universe's laws allow reversibility in equations, yet the universe proceeds as if it prefers forgetting, dispersing information into places no one can retrieve. So the most reliable direction in physics is the direction of lost details. A third irony rests gently behind them. Earth's oldest rocks are precious because they preserve information against the arrow of time, yet the same arrow guarantees that most of the early record is destroyed, so the planet's history becomes legible only through rare acts of resistance to inevitability. Only takes 1 billion years for rare to become almost none. The section lingers with Earth's slow irreversibility. Continental fragments once formed are altered by weathering and metamorphism, their minerals re-equilibrating under new pressures and temperatures. Isotopic systems in rocks can reset or partially reset, creating clocks that can be read carefully, but never without uncertainty. Zircons can retain core ages while their rims record later events like a layered memory, where older information persists inside newer rewriting. This is a lesser-known detail that is also a quiet lesson. Minerals can hold multiple time signatures, and interpreting them requires acknowledging that Earth does not store history in a single clean file. Only takes a crystal growing in stages to turn time into concentric rings. In the quantum realm, the measurement problem remains the scientific mystery in the background, but here a different uncertainty is allowed to sit beside it. Why does the universe begin in states that permit entropy, increase an entanglement growth in the direction we call future. The arrow of time is not only a local phenomenon, it is tied to cosmological initial conditions. Physics can describe how entropy increases given certain starting points, yet explaining why the starting point is low. Entropy is a deeper question. This is not speculative fiction, it is a recognized foundational issue in cosmology and statistical mechanics. The story holds it gently. Time's direction is experienced locally as irreversible processes, yet its ultimate origin may be tied to the universe's earliest conditions, which remain a place where explanation is incomplete. Only takes a single boundary condition in the far past to shape every irreversible event that follows. A gentle modern analogy can appear and fade. The spread of entanglement resembles dye dispersing in water, not because the physics is the same, but because the outcome is similar. An initially localized pattern becomes distributed until it is effectively impossible to reconstruct without impossible precision. The analogy is restrained. It does not claim equivalence, only a shared feeling of dispersal. Earth's oceans, with their mixing and currents, provide a literal example of dispersal, while quantum systems provide a formal one. Only takes mixing for a pattern to become a memory rather than a structure. The Archean planet continues to radiate heat into space, receiving sunlight in return, maintaining a dynamic, steady state that allows surface water. The ocean continues to circulate through crust, altering it irreversibly. The mantle continues to convect, bringing up melts and recycling material downward. In this constant motion, the arrow of time is not an extra layer. It is the direction all processes take when driven by gradients and constrained by the second law. Entanglement does not cancel this direction. It provides a deeper way to describe how correlations spread and how classical irreversibility emerges from quantum possibility. The section remains slow and even, leaving the sense that time is less a river than a tendency, less a path than a bias built into how energy and information move. Only takes a planet and a few fundamental laws for the future to become the direction in which details dissolve. Distance on the early Earth is measured in slow gradients rather than straight lines. Heat rises from deep interior to surface, carried upward through convection and melt, and then it leaves as radiation into space. Water moves from ocean to atmosphere and back, carried by evaporation and condensation, and its chemistry changes as it touches basalt, precipitates minerals, and returns altered. Carbon moves between air, ocean, and rock with a pace that is patient, uneven, and persistent. The planet's connections are tangible and causal. A process in one place changes conditions in another through transport of matter and energy. A scientifically accepted fact anchors the contrast that follows. Quantum entanglement produces correlations between measurement outcomes that cannot be explained by local hidden variable theories. Yet these correlations cannot be used to transmit information faster than light, because the outcomes on each side are intrinsically random, and the statistics observed locally do not depend on the distant measurement setting. This is the no-signaling principle as it appears in quantum theory. Entanglement does not allow superluminal communication. Only takes one counterintuitive phenomenon for the universe to add a safety rail. The story stays calm with why this matters. Entanglement can make two distant measurement records fit together with uncanny precision, but the record at one side alone remains indistinguishable from randomness. If one observer measures their particle, they see a sequence of outcomes with probabilities determined only by their local settings and the shared quantum state's reduced description. Nothing in that local sequence reveals what setting is chosen far away, and nothing can be done to force a desired outcome at a distance. The correlation appears only when results are later compared through ordinary communication that obeys light speed limits. The connection is real, but it is not a channel. only takes relativity's speed limit for quantum weirdness to learn manners. On Earth, distance is also policed by limits, though not the same ones. In the Archean Ocean, chemical signals disperse by diffusion and advection. A plume from a vent does not instantly alter the entire sea. In the atmosphere, photochemical products mix by winds and circulation. A volcanic outgassing event does not instantly shift global composition. In the mantle, heat and material move on timescales of millions of years. A deep thermal anomaly does not instantly produce a surface volcano. The planet is linked, but it is linked through transport delay and attenuation. Only takes viscosity, inertia, and diffusion to enforce patience. A poetic detail sits within these limits in deep ocean basins, far from surface waves. A disturbance can travel as a slow internal wave along density layers, invisible from above, carrying energy across distances without moving much water upward. A reminder that even in a seemingly still sea, there are hidden pathways that obey their own constraints. Only takes layering for motion to become subtle. The no-signaling rule is one of the quiet places where quantum theory and relativity coexist without conflict. Entanglement violates classical expectations about locality in the sense of predetermined properties, but it does not violate causal structure in space-time. This coexistence is not merely asserted, it is embedded in the mathematics of quantum theory and in decades of experiments. Yet the deeper relationship between quantum entanglement and space-time remains an open frontier, and the story keeps that as a quiet mystery rather than a claim. There are ideas in modern physics suggesting links between entanglement and geometry, especially in certain theoretical frameworks, but these are not settled in the way Bell tests are settled. Only takes a firmly established phenomenon to invite ambitious connections, and then caution becomes part of the discipline. The section stays grounded in the established entanglement correlations are strong, but they are not controllable in the way a telegraph signal is. In practice, protocols like quantum teleportation use entanglement plus classical communication to transfer an unknown quantum state from one system to another. The phrase teleportation sounds like a violation, but it is not. It requires a classical message to complete the transfer, preserving causality. The accepted fact is, precise quantum teleportation does not move matter and does not send information faster than light. It transfers state information using shared entanglement and classical bits. Only takes a name to make a careful protocol sound like science fiction, and then physics keeps the paperwork strict. Earth's own long-distance teleportations are chemical and geological, and they do not pretend to be instantaneous. Elements move from mantle to surface in magmas, then into sediments, then back into mantle, through subduction completing cycles that can take hundreds of millions of years. Water that circulates through crust can emerge changed, carrying dissolved metals from deep rock to ocean. The planet's surface composition becomes a record of these slow transfers. A lesser-known detail fits here. Some elements like boron and lithium are particularly sensitive tracers of fluid movement and alteration, and their isotopic ratios in ancient rocks can reveal interactions between seawater and crust long after the water itself is gone. Only takes a subtle isotope shift to preserve a memory of fluid pathways. 3 soft ironies settle into the contrast. First, the universe offers entanglement as an apparent shortcut correlation without contact, yet it forbids that shortcut from becoming a signal, so the most dramatic connection remains unusable for sending even a simple word. Second, Earth's most consequential communications, heat flow, carbon cycling water, circulation are slow and lossy, yet they reliably reshape the planet, while entanglement's correlations can be exquisitely precise and still fail to reshape anything unless harnessed in fragile setups. Third, human intuition worries about faster-than-light influence. while nature's actual fastest messengers, photons, spend most of Earth's early history being absorbed, scattered, and converted into heat and chemistry, as if speed is routinely traded for transformation. Only takes a planet to show that delay does not prevent consequence. The scientific mystery in this section can remain quiet but specific. Why does the world permit non-local correlations at all, and what do they imply about the structure of reality? The experimental facts are clear. Bell inequality violations, no signaling consistent quantum predictions, yet the explanatory picture differs across interpretations. Some interpretations accept non-locality in certain senses, others accept contextuality, others accept branching, others accept limitations on what can be said about unmeasured properties. No single story has been selected by consensus as the one true picture, even while the operational framework remains solid. Only takes a successful theory to create multiple compatible ways of speaking about it. On Earth, the parallel uncertainty is not philosophical but evidential. What exactly is the Archean atmospheric composition at different times and places, and how do we reconstruct it from mineral proxies, isotopes and sedimentary records that have been altered? The atmosphere leaves no direct samples from 4 billion years ago. It leaves only consequences. Sulfur isotope anomalies, paleosols, sediment, chemistry, and trace element signatures provide clues, but each clue depends on models and assumptions. The story keeps this as a calm reminder. Distance in time is another kind of separation, and reconstruction is always an act of careful inference. Only takes billions of years for the most important medium air to become a missing object. A gentle modern analogy can appear and fade. The no-signaling rule is like receiving a sealed envelope that is guaranteed to match another sealed envelope held far away, yet neither envelope reveals its content until opened, and opening one does not let anyone choose what is inside the other. The analogy is restrained and then released, because the physics is already clear in its own terms. Earth's gradients remain the closer reality, and the quantum rule remains a boundary that keeps the strange connection from becoming a faster route than light. The section ends with the sense that entanglement connects in a way that is simultaneously profound and limited, and that Earth's own connections, while slower and more ordinary, are the ones that reshape ocean's crust and climate over deep time. Only takes a strict limit to make a phenomenon feel both miraculous and politely constrained. Randomness on Earth is never pure. It is shaped by constraints by gravity, chemistry, temperature, pressure, and the planet's slow cycles, so that what looks like chance at one scale becomes pattern at another. In the Archean Ocean, turbulent mixing appears chaotic, yet it is bounded by density layers, heat flow, and the geometry of basins. In volcanism, eruptions can seem unpredictable, yet they follow the physics of melt generation buoyancy and fracture propagation. The planet's history is a long argument between disorder and structure often wins simply by being repeated long enough. A scientifically accepted fact sets the quantum side of this theme in standard quantum mechanics. The outcomes of individual measurements are intrinsically probabilistic, with probabilities given by the Born rule, and no known local hidden variable theory can reproduce the full set of quantum correlations observed in entanglement experiments. The randomness in quantum measurement is not presently explained as ignorance of underlying predetermined values in any local classical sense. Only takes a single electron to refuse to declare its future result until measurement, and then physics writes probability instead of certainty. This probabilistic character is not new to section 11, but here it is held in a more explicit contrast with the patterned outcomes that emerge from repetition. A single quantum measurement yields an outcome that cannot be predicted with certainty, yet many measurements yield a stable distribution. A single wave on the Archean Ocean is hard to predict, Yet the ocean's average behaviour shapes climate and chemistry in consistent ways. Randomness in both contexts becomes meaningful through aggregation. Only takes enough trials for unpredictability to settle into a curve. Entanglement adds a sharper edge. When two systems are entangled, their joint outcomes are not independent random variables. Each outcome remains individually random, but the pair is constrained. This constraint is what violates Bell inequalities and what distinguishes entanglement from classical correlation. The hidden order is in the joint statistics. It is an order that does not appear as a deterministic script for each particle, but as a pattern of conditional probabilities that is stronger than any local hidden variable model allows. This is the accepted fact in operational terms. Entanglement produces correlations that are irreducible to classical shared randomness under locality assumptions. Only takes two detectors and a shared source to turn randomness into a fingerprint of deeper structure. Earth, in its own way, also produces hidden order from what seems like randomness. In the Archean, chemical reactions in seawater are influenced by pH temperature and the availability of electron donors and acceptors. Even without invoking life, redox chemistry creates directionality. Reduced species tend to be oxidized when oxidants are available and energy is released. The environment provides gradients and constraints that shape reaction networks. If early microbes exist, they exploit these gradients, turning geochemistry into metabolism. But the story remains cautious about specifics and timing. The accepted process remains broader. Chemical systems under energy flow can develop sustained disequilibria, and those disequilibria can be maintained by continuous inputs such as hydrothermal heat and volcanic gases. Only takes a constant energy source to keep chemistry away from equilibrium. A poetic detail rests in the way the ocean holds metals. In an oxygen-poor sea, iron can remain dissolved and abundant, making the water in certain basins and at certain times faintly tinted when concentrated, though the effect is subtle and highly dependent on conditions. The iron does not announce itself as colour from the surface. It announces itself through later stone records and through the planet's readiness to react when oxygen appears. The ocean carries its future, precipitates invisibly. Only takes a dissolved element to wait in solution for hundreds of millions of years, and then the chemistry changes and it becomes rock. Three soft ironies settle into this section. First, the quantum world produces randomness as a basic output, yet that randomness is governed by an exact rule for probabilities, making unpredictability itself obey a strict structure. Second, Earth's early environments can look repetitive and steady in deep time, yet they are built from countless microscopic accidents, collisions, diffusion steps, fracture events, so the planet's stability is an emergent pattern made from uncountable small uncertainties. Third, humans often wish randomness would disappear in favour of certainty, while both Earth and quantum mechanics reveal that randomness constrained properly is one of the universe's most reliable ways of building patterns. Only takes enough time for chance to become a tool. A lesser-known real-world detail fits the theme of hidden order. In modern quantum experiments, randomness is not merely tolerated, it is used. Quantum random number generators exploit the inherent unpredictability of certain quantum outcomes to produce random bits that are in principle not predictable by any classical mechanism. Meanwhile, in Archean geology, randomness in mineral growth can encode environmental conditions. Crystal habits, zoning patterns, and inclusion distributions can reflect fluctuating conditions during formation, and careful analysis can extract signals about temperature and chemistry from what looks like irregular texture. The same broad principle holds noise can carry information when interpreted through the right model. Only takes a noisy pattern to become data once a theory exists to read it. The scientific mystery in this section remains pointed. Is quantum randomness truly fundamental, or could there exist deeper variables that are not local in the classical sense? or that evade certain assumptions used in Bell-type arguments. Some classes of hidden variable theories, such as non-local ones, are not ruled out in the same way, and other approaches shift which assumptions are considered acceptable. Yet the experimental evidence strongly constrains the simplest classical pictures. Another deep uncertainty remains in foundations, whether the Born rule itself can be derived from deeper principles in a way that is universally accepted, or whether it is simply a postulate that works with extraordinary consistency. Work continues in quantum foundations, but consensus on a single derivation or interpretation remains absent. Only takes a perfectly reliable rule to invite endless questions about why it is the rule. Earth's parallel uncertainty remains geological and chemical. The Archean rock record is sparse and altered and reconstructing global patterns such as the average ocean temperature, the atmospheric methane level, or the prevalence of certain tectonic regimes requires proxies that may be local and subject to later modification. Isotopic ratios in cherts and carbonates, for example, have been used to infer temperatures, but interpretations are contested because diagenesis and metamorphism can alter signatures. The mystery is not whether the Archean is warm or wet it is, but how warm, how variable, and under what exact atmospheric conditions. Only takes a metamorphic overprint to blur a thermometer. A gentle modern analogy can appear without insistence. Entanglement correlations resemble a duet, where each singer's notes seem improvised, yet the harmonies align more strongly than any pre-written local script would allow, even though neither singer can force the other to sing a chosen note at a distance. The analogy stays light and then dissolves, leaving the formal picture intact, randomness us locally, structure jointly. Earth's own duet is between disorder and constraint, between turbulence and thermodynamics, between mixing and gradients, where each local detail is unpredictable yet the long-term cycles are robust. The section remains slow with the idea that the universe is comfortable with uncertainty at the smallest scale while producing reliable patterns at larger scales, and that entanglement is one of the clearest demonstrations of how hidden order can be woven out of randomness without becoming determinism. Only takes probability to be structured for the world to become stable enough to study. Beneath the Archean ocean and its slowly changing atmosphere, Earth's mantle continues to move like a patient conveyor of heat and composition. It does not move quickly, and it does not move evenly, yet over millions of years it produces a persistent rearrangement of the planet's interior, feeding volcanism-altering crust and sustaining the conditions that keep surface water possible. The planet's deep circulation is a reminder that many body behavior is not a special case. It is the default. Earth is never just one thing interacting with one thing. It is countless degrees of freedom coupled together, exchanging energy and matter in a way that cannot be reduced to a single simple narrative without losing the truth of its complexity. A scientifically accepted fact anchors the quantum parallel. Many-body quantum systems can exhibit entanglement across large numbers of particles, and the patterns of that entanglement help explain collective behaviors such as thermalization phase transitions and the emergence of effective classical properties. In certain quantum materials and models, entanglement is not a rare link between two particles. It is a network-like structure spread across an entire system. Only takes a crowd of particles for pairwise to become inadequate. The section lingers with the idea of networks first in stone and then in quantum matter. In the mantle, convection creates an evolving network of upwellings and downwellings. Hotter, buoyant material rises in plumes or broader currents. Cooler, denser material sinks. These motions are constrained by viscosity phase changes and the arrangement of the lithosphere above. In an early Earth with higher internal heat convection may be more vigorous, the lithosphere thinner and more mobile or more prone to episodic overturn depending on the regime. The uncertainty remains real. The detailed style of Archean mantle convection and tectonics is still debated. Only takes one uncertain parameter, viscosity, as a function of temperature and composition to change the entire style of a planet's surface recycling. A poetic detail rests in what convection implies the mantle is solid rock, yet over long times it flows like a fluid, meaning Earth carries an ocean of stone whose waves are thousands of kilometers wide and whose periods are measured in tens of millions of years. Only takes patience to see solid rock behave like water. Entanglement networks in many body systems are different in mechanism, but similar in mood. The whole cannot be described as a simple sum of independent parts. In a strongly interacting quantum system, measuring or perturbing one region can affect correlations with many others, and the distribution of entanglement can determine how information spreads and how the system approaches equilibrium. In modern physics, concepts like entanglement, entropy, area laws, and scrambling describe aspects of these networks. The details can be technical, but the accepted core remains. Entanglement structure is a real property of quantum states, and it shapes observable behavior, especially in complex systems. Only takes interaction for entanglement to proliferate. Earth's ocean too becomes a network. Currents connect basins. Hydrothermal circulation connects seafloor to seawater chemistry. Weathering connects land to ocean via rivers and dissolved ions, even if land is limited and often submerged or volcanically young. The atmosphere connects globally through circulation and mixing. In a young Earth, these networks are more chemically reducing and more volcanically forced, yet they are networks nonetheless, and they allow distant regions to influence one another through transport rather than instant action. A lesser-known real-world detail fits here in modern oceans. The deep overturning circulation can take on the order of 1,000 years to complete a global loop, while in the Archean, the exact patterns are unknown. Yet the principle that oceans can connect the planet on timescales longer than weather, but shorter than tectonics, remains. Only takes a basin and a density gradient for water to become a slow messenger. Three soft ironies settle gently into the comparison. First, the most complex systems are often the ones that look the simplest from afar. Earth appears as a blue sphere, calm and coherent, while its interior is a tangled flow of heat and composition, and many-body quantum systems can appear as uniform materials while hiding elaborate entanglement patterns. Second, entanglement is introduced as a strange connection between separated particles, yet, in many-body systems, it becomes so common that separability is the exception, making the weird thing the default in the microscopic crowd. Third, the universe forbids faster-than-light signaling through entanglement, yet it allows information to spread extremely quickly within many-body systems through scrambling, meaning nature is careful about the speed of messages across space, while being generous about the speed of mixing inside a crowded system. Only takes strict rules in one category for freedom to appear in another. The scientific mystery in this section can remain quiet but specific. How exactly does thermal behavior emerge from unitary quantum dynamics in large systems? And what role does entanglement play in making subsystems look thermal, even when the overall system is in a pure state? The eigenstate thermalization hypothesis and related ideas provide strong frameworks and evidence in many contexts, yet there are exceptions. Integrable systems, many-body localized systems where thermalization can fail or be altered. Understanding the boundary between thermalizing and non-thermalizing behavior remains active research. The mystery is not whether many systems thermalize, they do, but why the rules take the shape they do across different classes of systems. Only takes one system that refuses to thermalize to keep the question alive. Earth has its own refusal cases. Not all parts of the planet mix efficiently. Chemical reservoirs can remain distinct for long times, preserved by limited exchange. Certain isotopic signatures suggest that parts of the mantle may retain ancient heterogeneities despite billions of years of convection. The persistence of such heterogeneities is an active area of geochemistry and geodynamics, tied to how mixing occurs, how plumes sample deep reservoirs, and how subducted material is stirred. The planet, like a many-body system, does not necessarily reach perfect equilibrium. Only takes a slow convecting mantle for some memories to survive longer than expected. A gentle modern analogy can appear and then fade. The mantle's convection resembles a slow stirring of thick batter, where some streaks remain visible long after stirring begins, while others blend quickly and the final texture depends on viscosity, temperature, and the pattern of stirring. The analogy is restrained and then released because Earth's interior is not a kitchen, and its physics is different, yet the feeling of imperfect mixing is real. In quantum many-body systems, entanglement spreading can similarly be rapid in some regimes and constrained in others, with certain structures persisting. Only takes constraints for mixing to become incomplete. The section remains grounded in Earth's deep time, as it notes that many-body behavior is not a human invention of complexity. It is the default state of the physical world. The Archean planet is a coupled system of mantle, crust, ocean, and atmosphere, each influencing the others through flows and feedbacks. The quantum world beneath every bond and lattice is also a coupled system where particles interact, entangle, and collectively produce phases of matter and thermal behavior. The connection that breaks physics begins as a pairwise surprise, but in the many-body view it becomes a kind of fabric so common that the challenge becomes not creating it, but understanding its structure and controlling it. Earth's own fabric is stone and water and gas woven by heat and gravity into patterns that persist without being still. Only takes a crowd of interacting parts for the whole to become its own thing. Earth keeps learning how to be useful to itself, in the plain physical sense that certain structures once formed make later processes easier to sustain. As time moves beyond the Archean toward the early Proterozoic, the planet's surface becomes less uniformly volcanic and more varied in its textures of stability. Continental crust grows in volume and in persistence, built through repeated melting, accretion, and reworking, and it begins to stand higher above sea level in broader regions, not permanently but often enough to matter for weathering and sediment delivery. A scientifically accepted process anchors this shift. Continental crust forms and evolves through partial melting, magmatic differentiation, and tectonic assembly, producing rocks that are on average more silica-rich and buoyant than oceanic crust, allowing continents to persist as long-lived platforms even while being continuously modified. Only takes compositional buoyancy for a piece of crust to resist being swallowed quickly, and then it becomes a scaffold for new kinds of surface chemistry. The oceans continue and the atmosphere remains largely oxygen-poor compared to the modern world, though subtle changes accumulate in redox balance and in the cycling of sulfur, iron, and carbon. Weathering becomes a more influential editor as land surfaces appear and vanish, pulling carbon dioxide from the air through chemical reactions with silicate minerals and delivering ions to the sea. The planet's long feedbacks strengthen not because they become perfectly stable, but because they become persistent enough to be called a system rather than a sequence of accidents. A poetic detail rests in the way rivers begin to matter when rainwater meets fresh rock. It carries dissolved silica and metal ions downstream, and in quiet basins the water can lay down thin laminations of sediment that settle as softly as dust, stacking into layers that look much later like the planet's slow handwriting. Only takes a calm basin for erosion to turn into archive. In the quantum story, the word useful arrives with a similar calmness, and it changes the tone of entanglement without changing its physics. Entanglement is not only a surprise in correlation experiments, It is also a resource, something that can be spent to achieve tasks that are impossible or less efficient with classical correlations alone. This is a scientifically accepted fact in quantum information science. Entanglement enables protocols such as quantum teleportation, entanglement-based cryptography, and certain forms of quantum computation and sensing, and it can be quantified, generated, consumed, and degraded by noise. Only takes an abstract connection to become a practical tool once it is understood as a measurable commodity. The story stays slow with what resource means. It does not mean energy in the thermodynamic sense. It means a property of shared quantum states that can be harnessed to perform operations in information processing tasks. A pair of systems that share entanglement can coordinate outcomes and transfer quantum state information in ways not achievable by shared classical randomness alone, provided classical communication and suitable operations are also available. In quantum teleportation, for example, an unknown quantum state is transferred from one system to another using an entangled pair and a classical message that communicates the result of a joint measurement. The classical message is essential so no speed limit is broken. The entanglement supplies the non-classical structure that makes the transfer possible without physically sending the state carrier itself. Only takes the right bookkeeping to move a state without moving the thing that originally holds it. Earth's Proterozoic tendency toward longer-lived surface environments becomes a fitting companion to this resource framing. Long-lived continental shelves and shallow seas support sedimentation patterns that can preserve chemical signatures over vast timescales. The seafloor continues to host hydrothermal systems, but the surface now also hosts more stable basins where sediments accumulate in thick sequences. In these sequences, geochemists later read changes in ocean chemistry, redox state and atmospheric composition through isotopes and mineral assemblages. A lesser-known detail fits with quiet precision. Certain trace metal abundances in shales such as molybdenum and uranium can be sensitive to the presence of oxygenated conditions in seawater, allowing ancient sediments to act as indirect records of redox landscapes, though interpretation is careful and often contested. Only takes a few parts per million of an element in mud to become billions of years later a clue about the sky. The resource theme also highlights fragility. Entanglement can be created, but it can also be lost, and the loss is not dramatic. It is usually mundane. Thermal noise scattering, absorption, material defects, and timing jitter all erode entanglement. This is why quantum technologies are often described in terms of protecting a resource from a world that constantly tries to disperse it into untracked correlations with the environment. In this sense, entanglement resembles a delicate reserve held in a leaky container, and engineering becomes the craft of patching leaks. Only takes a few stray interactions to spend the resource without meaning to. Earth's own resources are also leaky in their own way. The planet builds continents and then erosion wears them down. It builds atmospheres and then space and chemistry remove parts of them. It accumulates heat and then radiates it away. The difference is that Earth's resources are replenished by deep cycles. Volcanism returns gases. Tectonics rebuilds crustal thickness in places. Sedimentation and burial store carbon and other elements, and later metamorphism and melting return them. The planet's usefulness is not static, it is maintained by flux. A gentle modern analogy can appear and then fade. Earth's long carbon cycle behaves like a planetary budget that is balanced not daily, but over hundreds of thousands to millions of years, with deposits, withdrawals, and interest paid in weathering rates and volcanic outputs. The analogy remains restrained, because the real process is already clear in its own terms. Only takes long timescales for a budget to look calm. 3 soft ironies settle into this section, without breaking its stillness. first entanglement is often treated as the most exotic feature of quantum theory, yet as a resource it becomes something counted, traded, and managed, meaning the strangest connection is turned into a kind of accounting entry. Second Earth's most visible resources like continents and oceans exist because the planet continually wastes energy radiating heat into space and dissipating gradients so stability is purchased by relentless loss. Third, the technologies built to use entanglement often require extreme conditions, ultra-cold temperatures, vacuum shielding, while Earth's own long-term stability is achieved through openness and mixing, so the resource is protected by isolation, while the planet's habitability is protected by exchange. Only takes opposite strategies to reach the same goal of persistence. The scientific mystery in this section is quiet but specific. What are the ultimate limits of entanglement as a usable resource at scale, and how do those limits depend on noise error, correction overhead, and the physical platform? Fault-tolerant quantum computation, for example, is supported in principle by rigorous theory showing that error correction can suppress errors below a threshold if physical error rates are low enough, and if sufficient redundancy is used, yet the practical path to large-scale devices remains an open engineering frontier. Similarly, long-distance quantum communication through entanglement distribution faces challenges from photon loss and decoherence motivating concepts like quantum repeaters, which are still under active development. The uncertainty is not whether the ideas are sound in theory, but how efficiently and how broadly they can be realized in practice. Only takes one stubborn noise source to make a clean threshold feel far away. Earth's parallel mystery remains in the realm of deep-time transitions. When and how does the planet cross into conditions that allow a sustained rise of atmospheric oxygen, and how do tectonics, nutrient cycles, and biological activity interact to make that possible? The great oxygenation event lies in the Proterozoic, but the preparatory steps begin earlier in the slow accumulation of redox changes, the burial of organic carbon, and the evolving balance of volcanic gases and weathering inputs. The details remain debated: the timing of oxygen oases, the role of methane, the pace of ocean oxygenation, and the feedbacks that stabilize or destabilize oxygen levels. The rock record offers strong constraints, yet it also offers room for multiple pathways. Only takes a planet-wide chemical shift to leave many signatures, and still it refuses to reveal every step in order. The resource theme lingers then in two domains that do not pretend to mirror each other, but share a quiet structure. Something valuable exists. It is fragile. It can be replenished or protected under certain conditions, and it enables transformations that would not otherwise occur. In the quantum domain, entanglement enables protocols that reshape what information can do. In the planetary domain, long-lived continents, oceans, and cycles enable transformations in atmosphere and surface chemistry that set the stage for later complexity. Both are built from deep physics, and both are constrained by noise, thermal noise in one case, geological and chemical churn in the other. Only takes the right kind of persistence for a resource to become a turning point without announcing itself as one. Earth moves into the Proterozoic with a steadier face, not because its interior stops convecting or its crust stops breaking, but because its most planet-wide cycles become easier to recognize as cycles. Oceans persist as a dominant surface feature, continents occupy larger areas and endure longer, and the atmosphere becomes a more legible participant in long feedbacks between rock, water, and air. The planet still changes, but the changes increasingly appear as shifts in balance rather than constant reinvention. A scientifically accepted fact sits at the center of this steadier era. The Great Oxygenation Event occurs in the early Proterozoic, when atmospheric oxygen rises from extremely low levels to significantly higher ones, driven ultimately by oxygenic photosynthesis and modulated by sinks such as reduced volcanic gases and the oxidation of oceanic and crustal materials. The rise is not a single moment and not a clean step. It is a transition recorded in multiple lines of evidence, including the disappearance of mass-independent fractionation signatures in sulfur isotopes and the appearance of oxidized minerals in sediments. Only takes a few molecules of oxygen to be chemically decisive, and it takes hundreds of millions of years for them to become steadily abundant. The atmosphere is still not modern. Oxygen remains lower than present-day levels for long stretches of the Proterozoic, and the oceans may remain largely anoxic in deeper waters with complex redox stratification. Yet the direction has changed, and with it the chemistry of the surface changes in ways that cannot be quietly undone. Dissolved iron that once circulates freely in anoxic seawater now finds a new fate. It oxidizes, precipitates and settles, building extensive iron-rich sediments. The poetic detail is that the planet's great mineral archives begin to assemble in bands thin layers of iron oxides, alternating with silica-rich layers, creating banded iron formations that look much later like slow, disciplined striping across stone, as if the ocean spends ages learning to write in alternating lines. Only takes a changing redox boundary for an entire ocean's dissolved load to turn into layered rock. This is Earth's side of the section's theme, a transition that is both chemically simple and historically immense, a shift in what the environment permits. The uncertainty remains quiet but real because the oxygen story is not only about production, it is about balance. How much oxygenic photosynthesis exists before the atmosphere responds? How patchy are early oxygen oases near microbial mats? How does methane produced by anaerobic microbes interact with rising oxygen, and what does that do to climate? How quickly does the deep ocean respond, and what are the timescales of mixing and ventilation? The rock record offers constraints, but it does not provide a continuous monitor. Earth's oxygenation becomes a deep-time reconstruction problem, where multiple models can fit parts of the evidence and still disagree on the details of pacing and spatial structure. Only takes a few missing intervals in the record for the most consequential transition to remain partly out of focus. In the quantum story, the section turns toward what physics still cannot say, with the same confidence it says Bell inequalities are violated or no signaling holds. Entanglement is all experimentally real and mathematically defined, yet its meaning depends on how the theory is interpreted, and its relationship to other foundational pillars remains incomplete. A scientifically accepted fact that is safe and central here is that different interpretations of quantum mechanics, such as objective collapse approaches, many worlds type approaches hidden, variable approaches with non-locality and epistemic or relational approaches are constructed to reproduce the same standard quantum predictions in ordinary regimes, which is why they coexist. The predictive machinery does not on its own select a single picture of what the wave function is, only takes one formalism that works too well for multiple stories to gather around it. The section remains calm and specific about the open questions that persist without turning them into spectacle. One question concerns measurement: why and how does a definite outcome appear in any single trial, and what precisely counts as a measurement interaction in physical terms? Decoherence explains the practical loss of interference and the emergence of stable records, but it does not by itself force a unique outcome in every interpretive framework. Another question concerns randomness, whether the Born rule is fundamental or derivable from deeper principles in a universally compelling way. Another question, perhaps the most widely recognized frontier, concerns gravity. How entanglement and quantum theory integrate with space-time dynamics in a complete theory of quantum gravity, and whether space-time geometry might in some way reflect patterns of entanglement in underlying quantum degrees of freedom. The story does not claim a settled bridge. It holds the uncertainty, as it is a place where powerful hints exist but no consensus completion. Only takes the success of quantum mechanics to make its unification gaps feel sharper. Earth provides a steady counterpoint to these conceptual gaps through its own transformation. The rise of oxygen changes mineral stability fields across the surface. Oxidized minerals become common. The weathering regime changes. Ultraviolet shielding increases as ozone can form when oxygen is present, altering photochemistry and surface radiation environments. These are grounded consequences, and they echo the section's larger motif. A new background condition can make entirely different processes feasible without introducing any new laws. In the quantum case, a new conceptual framework might be needed to make measurement and gravity sit together comfortably. In Earth's case, a new atmospheric composition reshapes the surface without changing physics' only boundary conditions. Only takes a different atmosphere for the same sunlight to become a different chemical force. 3 soft ironies settle into this section as gently as sediment. First, entanglement is described as a connection that breaks expectations, yet the most dramatic violations of classical intuition arrive as statistical regularities that require patience and repetition to see meaning. The shock of non-classical reality is delivered through calm averages. Second, the Great Oxygenation Event is often framed as a biological revolution, yet from the planet's perspective it is also a long geochemical bookkeeping shift sources and sinks slowly rebalancing, so a transformation that changes the surface forever can proceed without urgency, as if Earth is reluctant to hurry even when it is rewriting its atmosphere. Third, human minds often search for a single explanation of quantum foundations, while Earth's oxygen history suggests a more familiar pattern. Major transitions can have multiple coupled causes and feedbacks, and this record rarely yields a single tidy storyline. Only takes a complex system for neat answers to become rare. A lesser-known real-world detail fits the oxygen transition with quiet accuracy long before oxygen becomes abundant in the air. Certain minerals in ancient soils and sediments can preserve clues about local redox conditions, and geochemists use proxies such as chromium isotopes and trace metal patterns to infer oxidative weathering and oxygen presence in parts of the surface system. These proxies are subtle, and their interpretation is careful, but these show how indirect the evidence must often be when the medium itself, ancient air, cannot be sampled. Only takes a few atoms arranged differently in a mineral to store a clue about an atmosphere long vanished. In the quantum world, an equally subtle detail appears in the way entanglement is quantified and detected. In complex systems, entanglement is not always revealed by simple two-point correlations. It can require more sophisticated witnesses, tomography, or entanglement entropy, estimates that are difficult to access experimentally. The resource is real, but its measurement can be indirect and expensive, and practical systems often rely on partial certification rather than complete state knowledge. This is not a weakness, it is a consequence of complexity. Only takes a large Hilbert space for complete knowledge to become unrealistic. The scientific mystery held in one quiet place can now be stated without pushing if entanglement is as fundamental as experiments indicate what is its deepest role in shaping the classical world and space-time itself. Does it merely describe correlations between subsystems, or is it also a structural ingredient in how reality is stitched together at the most basic level? Physics does not yet offer a single consensus answer. It offers multiple lines of inquiry, quantum information approaches to thermodynamics, efforts toward quantum gravity, ongoing experimental tests of macroscopic superpositions and collapse models, each narrowing possibilities while leaving the central question open. Only takes an unanswered why for an answered how to feel incomplete. Earth's own central why remains nearby, Why does oxygen rise when it does, and why does it rise in the particular pattern the rocks suggest, rather than smoothly or immediately? The planet's answer seems to involve thresholds and feedbacks, biological production burial of reduced carbon, diminishing sinks, tectonic influences on nutrient supply, yet the precise choreography remains debated. The section allows that unresolved choreography to remain because deep time is not obligated to provide a clean timeline. Earth becomes calmer in the sense that its surface conditions stabilize enough to host longer-lived environments, but it is not calm in the sense of being finished. It continues to evolve, and it continues to keep parts of its story behind mineral veils. Entanglement similarly becomes a mature and usable concept while still leaving foundational questions open. The connection does not break physics by defeating rules. It breaks it by forcing physics to admit that its rules can be satisfied in more than one conceptual picture and that some pictures remain unfinished. Only takes a universe that is consistent in outcomes to be difficult in interpretation. Earth continues past the great oxygenation event into a Proterozoic that is long, spacious, and often understated, a stretch of time where the planet is neither young nor modern, neither wholly alien nor comfortably familiar. Oceans remain dominant. Continents continue to assemble, fracture, and reassemble. The atmosphere carries oxygen as a persistent component, now yet the oceans are not uniformly oxygenated, and deep waters can remain chemically stratified, sometimes rich in sulfide, sometimes rich in iron, sometimes simply low in oxygen, depending on circulation and nutrient supply. The planet's surface becomes a layered system of zones, each with its own constraints and each responding to the same sunlight and the same gravity in different ways. A scientifically accepted fact anchors the closing section. Earth's oxygenation is not a single completed event, but a multi-stage process with oxygen levels fluctuating and rising further later in Earth history, while the Proterozoic hosts significant climate episodes such as Snowball Earth, glaciations in the Neo-Proterozoic indicating that even with oxygen present, the climate system can still tip into extreme states under the right conditions. Only takes a small shift in feedbacks for an ocean world to consider ice. This late Proterozoic possibility sits as a reminder that stability is always conditional. Earth's habitability is maintained by balances that can be perturbed. Greenhouse gases rise and fall. Continents influence weathering and albedo. Biological activity alters carbon cycling. The planet keeps working within constraints rather than resting in a final state. The poetic detail is quiet and physical when ice advances over oceans and continents. It changes how the planet reflects light. And even before a global glaciation, expanding ice in higher latitudes can brighten Earth from space, making it appear in the long average a little more reflective, as if the planet is learning a paler expression. Only takes more ice for the same sunlight to do less warming. The story does not rush into Snowball Earth itself. It uses the mention as a distant horizon of the Proterozoic system's capacity for extremes, and then it returns to the present theme, a planet settling into layered long-lived cycles, and a concept entanglement settling into a precise place in physics, while leaving certain foundational questions open. Entanglement has been introduced as a connection that violates classical locality assumptions without violating the no-signaling constraint. It's been shown to be fragile under decoherence, yet robust enough to be engineered into a resource. It has been widened from pairwise links into many-body networks that help explain thermalization and emergent classicality. Now the story holds the final unresolved edges without drama. A scientifically accepted fact that can be stated plainly here is that entanglement is a well-defined property within quantum theory, measurable through correlations and quantifiable by various entanglement measures, and it is indispensable in modern quantum information science. yet a complete experimentally confirmed unification of quantum mechanics with gravity and a universally accepted interpretation of measurement remain open problems. Only takes a mature field to admit where its foundations are still being repaired. The section remains slow with what remains uncertain, and it does so by naming the uncertainty rather than filling it. Quantum mechanics predicts with extraordinary accuracy, but it does not settle by prediction alone. What the wave function represents physical reality information or something else. Decoherence explains why classical behavior emerges, but it does not by itself provide a single agreed story of why one outcome is experienced in each measurement event. Experiments push quantum coherence toward larger masses and longer times, constraining some collapse models and reinforcing standard predictions, yet the interpretive landscape remains plural. The relationship between entanglement and space-time geometry appears suggestive in certain theoretical frameworks, but the step from suggestive to experimentally demonstrated is not yet completed. Only takes one missing experimental bridge to keep a powerful idea in the realm of research rather than settled fact. 3 soft ironies settle into this closing section as gently as dust on quiet water. First, entanglement is often introduced as if it breaks physics, yet it does so by obeying physics more faithfully than classical intuition expects, never stepping outside the mathematical rules even while forcing common sense to retreat. Second, Earth's long Proterozoic calm is often overlooked because it lacks the obvious drama of earlier formation or later animal diversification. Yet it is during this long interval that the planet's atmosphere, climate, and chemical cycles become the stable stage for everything that follows. Meaning, the most consequential preparation happens in the least celebrated span. Third, the more precisely entanglement is measured and controlled, the more clearly its limitations appear. No signalling fragility under noise-heavy engineering demands. So the universe offers its strangest connection with strict guidance labels attached. Only takes precision to reveal constraints. A lesser-known real-world detail fits the late Proterozoic, and the theme of layered systems. Even after oxygen rises in the atmosphere, the oceans can remain redox stratified for long periods with oxygenated surface waters above and anoxic deeper waters below, and this stratification can leave signatures in trace metals and isotopes preserved in sediments. The ocean, even in an oxygenated world, can keep secret zones where different chemistry rules, a quiet reminder that global averages hide local realities. Only takes a density gradient and limited mixing for the deep ocean to become its own chemical province. In the quantum domain, a similarly subtle detail is that entanglement is not a single monolithic quantity. Different kinds of entanglement exist, and their usefulness depends on context. Bipartite entanglement between two systems differs from multipartite entanglement spread across many. Some entanglement can be distilled into purer forms. Some is bound and cannot be distilled under certain operations. These distinctions are technical but real, and they show how connection can have different grades and shapes even within the same formalism. Only takes complexity for one word to hide many categories. The section maintains a steady gaze at the idea that Earth too learns categories the hard way. Continents differ from oceanic crust. Shallow seas differ from deep basins. Oxygenated surface waters differ from anoxic depths. The atmosphere becomes layered with different photochemical regimes. The planet's present-day habitability is not a single condition, but a stack of regimes balanced over time. The connection theme is held gently. Earth is connected by cycles that move carbon, water, and heat through its system, while entanglement connects quantum systems through joint states that cannot be decomposed into independent parts. The two forms of connection are not equated yet. They share a quiet structural likeness. Neither connection is visible from the parts alone, and both are best seen by looking at relationships rather than isolated objects. Only takes a relational view for the world to become legible. The scientific mystery that remains at the very end is left deliberately unresolved, whether entanglement is merely a feature of quantum description, or whether it is a deeper ingredient in the architecture of reality that might one day clarify measurement and unify with gravity. Earth's corresponding mystery remains how the planet's long-term cycles tip into global states like snowball Earth, or into oxygenation thresholds, and how tightly these transitions are coupled to tectonics biology and atmospheric chemistry. In both cases, the answer is partially known and partially hidden, constrained by evidence and by the difficulty of recreating ancient conditions or proving Planck-scale physics. Only takes a boundary of knowledge for the known to feel more precious. The narrative reaches its last outward motion by returning to stillness as a physical condition rather than an emotional one. Earth in this long Proterozoic quiet continues to rotate and orbit. The magnetosphere continues to sculpt charged particles. The oceans continue their slow exchanges. The planet's surface remains a place where stone, water and air meet and trade atoms. And within every atom the quantum world continues to permit entanglement, while the warm, busy environment continues to erase it unless it is carefully protected. The connection that breaks expectations remains real, disciplined, and unfinished in explanation. The planet remains real, disciplined, and unfinished in its transitions. Neither needs to conclude. They simply persist. The voice slows without changing its calm, and the motion of explanation loosens its grip. Earth is still a planet in constant exchange, but it is no longer necessary to follow every exchange to its next step. The oceans continue their long circulation, lifting heat from the crust and carrying it into wider basins, then letting it go again to the air. The continents continue to stand wear down and rise in new forms, their minerals breaking and recombining under rain and time. The atmosphere continues to breathe in a purely physical sense, taking in gases from volcanism and releasing others through weathering, burial and escape while sunlight arrives and leaves again as infrared, a steady trade across the top of the sky. The planet does not pause yet. It begins to feel like it can be left alone for a moment, trusted to keep turning without being watched. Only takes 4.5 billion years for ongoing to look like a kind of rest. In the smallest scales, beneath all of this entanglement remains what it has been. Throughout the story, a shared quantum state that binds outcomes without becoming a message, a correlation that refuses classical locality, yet obeys causality with strict patience. It persists where conditions allow it and dissolves where conditions do not with drama, but with the quiet inevitability of interaction. The strangeness remains, but it no longer demands attention. It becomes part of the background rulebook, like gravity, like thermodynamics, like the uncounted molecular collisions in seawater. The open questions remain open, and they do not need to be closed tonight. Measurement still has its quiet edge of uncertainty. Gravity still waits for a fully settled quantum story. The reasons for the universe's particular starting conditions still rest in deep cosmological silence. Only takes a working theory for mystery to be allowed to continue. Earth's surface settles into images that do not push forward. A dark ocean holds a faint sheen under angled light. A broad, quiet shelf receives slow sediment grain by grain, each grain a small surrender to time. A distant volcanic ridge releases heat into water that carries it away without notice. Above the atmosphere is a thin gradient rather than a wall thinning into space where fields remain and nothing is truly empty. The planet's glow in infrared continues a steady loss that makes life and weather and long cycles possible. The whole system is held in balance by ceaseless, gentle waste of energy, a calm dissipation that never finishes, only takes continual loss for a world to remain habitable. The story releases its last need to connect ideas. Stone is stone, water is water, light arrives and leaves. Correlations exist where they exist. Noise returns where it returns. The planet rests not by stopping, but by repeating the same patient motions that have carried it from molten beginnings to layered oceans and air. The connection that once felt like it broke physics remains simply one of physics' quiet permissions, a rule that holds even when it is not observed. And Earth, turning beneath a steady star, continues to be the place where rules become landscapes and time becomes layers.